Okay, I want to make a video to show how the dimensions of Earth basically prove that the Earth is flat. The diameter of Earth, here we've got the diameter of Earth is 12,742 kilometers. Okay, so on my little diagram here we've got it 12,742 kilometers is the diameter. Okay, so what we want to work out, well, the radius is 371 kilometers, which is from the center to the outside. That's because it's half of the diameter. You can even have a look here. Basically says here the radius 6,371. So basically we want to work out the circumference of Earth. Okay, so what we do is we get the diameter, we times that by pi. So if you get the diameter, which is 12,742, and then we'll times that by pi times 3.14159265359 equals 40,030 kilometers, 0.173, whatever that is. It basically meters. So we're basically working on 40,000 kilometers the circumference. So basically all the way around is 40,000 kilometers. Okay, so basically from here to here is what we want to work out, which is 10,000 kilometers, 20,000, 30,000 and 40,000 kilometers. Okay, so for the 10,000 kilometers that you're going around here, you're actually decreasing in altitude of 6,371 kilometers, because that's basically the drop. If you were to fly a plane directly flat on the horizon as you were where you are, you'd have to adjust for the decrease in altitude, which is 6,371 kilometers. Well, if we work that out to feet, one foot is 0.0. We'll actually go the other way around, kilometers to feet. And 1 kilometer equals 3,280 feet. Okay. The 6,371 kilometers in drop. Basically from here to the center, from here to here, which is 10,000 kilometers from there to there, but you're decreasing in altitude of 6,000 kilometers. Okay, well, if we times that by feet, times that by the 6,000 kilometers, because 1 kilometer is 3,000 feet, so we'll times that by 3,280 equals 20 million feet, 896,880 feet. So 6,000 kilometers, or 6,300 kilometers is 20,896,880 feet. So that's the adjustment that they would need to make to basically fly from here, point A, to point B. It's basically a 20 million feet drop that you'd have to adjust. Thanks for watching. Yeah, I just wanted to make a video to show how the round Earth model is all flawed, and basically what people aren't actually observing when they're looking at pictures. Okay, if you have an Earth is just like a clock. It spins 360 degrees for 24 hours. So for an example, there's Australia, 12 o'clock at Australia in the daytime, because morning would be there and nighttime would be here. So roughly 12 o'clock. Well, when this spins 360 degrees for 24 hours, it comes to the same direction, the same spot. Okay, it doesn't go 361 degrees, 360, it's 360 for 24 hours. It doesn't go 359. Okay, so when that's spinning around the sun, 24 hours is always going to be pointing that way, forward. This is backwards, forwards, left and right. Okay, not north, south, east and west, forward, backwards, left and right. And by that time that keeps going forward, spinning around, 24 hours is always forward. So by the time it comes around here, the sun is on the back of the earth. So therefore 12 o'clock in the afternoon on this side is going to be 12 o'clock at night time. Okay? Same vice versa, when it's going around 3 months, you're going to have sun on the side of the ball when 12 o'clock should be at here. The sun should be shining here at 12 o'clock because 24 hours is 360 degrees. If you can't work that out, well, go look how a clock works. Scale of the sun to the earth, well, if you look at 1 centimetre equals 1 million kilometres, the distance to the sun is 149 million kilometres, so therefore it works out to 149 centimetres. The size of the sun is 1.3 million kilometres, so therefore the sun would be 1.3 centimetres. So basically the sun is 1.3 centimetres, and then we go all the way down to the earth, and the earth is 1/10 of a millimetre, because 1 millimetre is 100,000 kilometres if 1 centimetre equals a million kilometres. So therefore the earth is 1/10 of a millimetre. So it's basically a dot. Now if you put that in comparison to what you're actually looking at, I don't know how a 1 centimetre marble would heat up a little dot 149 centimetres away. I don't know how you get a hot spot and a cold spot on that little dot from what we're looking at. Thanks for watching. Okay, I wanted to make a video to prove and show how the Earth is stationary. You'll see the pole star, it stays in the centre of the rock. The stars spin around. Okay, here is another one. Pole star stays in the centre, the stars spin around. Now I'll show you what happens if the Earth moves and Polaris moves. Put you on my little experiment. Okay, the stars are perfectly positioned to make a circle. If you have the stars just randomly anywhere, they don't make perfect circles. And when you spin Polaris, you'll see that the stars spin perfectly in circles, and that's Polaris spinning. Okay. Now we'll move the Earth. This is what happens when the Earth spins. The camera is designed to do a 10 centimetre circle. See how Polaris, the pole star, doesn't stay in the centre where the rock is. Okay? And the problem with that, what you're seeing there, the Earth is not moving. Nothing is moving where the camera is and the circle here. The camera's not moving, Polaris is spinning around. It's stationary. We will stop that for a minute and turn the Earth around. You don't get a pole star. You can spin that around all day, you will not get a pole star. There's another problem. There's 3 problems with that. The pole star doesn't line up if the Earth moves. It goes out of centre and keeps going around. There's another problem with it. You can spin it around full 360 degrees. We get back to the bowl in the middle and you can spin it around again. Well, we've just done 2 days of circles. Nighttime is only 12 hours of a circle. So then therefore you're only doing a half a circle. It would look like a friggin' rainbow. That's all you would see. Well, the thing is, you can do a time lapse of Polaris in 1 hour. which is 1/24th of a circle, which is only about there. That's what you get. You don't get any spinning of Polaris in a stationary motion spinning around a pole. There's your 1 hour, 1/24th of a circle. How does your gravity work on a stationary Earth? This proves Earth is stationary. Anyone can make a Polaris, spin it around, have a camera stationary, and you will see the camera is stationary. It does not move. Polaris spins. Thanks for watching. I was told today that compasses don't work on electromagnetism. Well, here is the compass sitting on the concrete. Okay, I'm about to put 1.2 volts of electromagnetism out of a 1.2 volt AA battery and a piece of wire to make an electromagnet. No, they don't work on electromagnetism. Zoom out a little tiny bit so you can see. The polarity of which way the energy flows is which way the compass flows. And this is only a 1.2 volt battery, which has very little electromagnetism. But yeah, it'll move a compass. Thanks for watching. Okay, I wanted to make another video to show that the stars spin and the Earth is dead stationary. I mean, which way is the Earth spinning in that picture? It's definitely not spinning. From the camera to Polaris is stationary. It's still, it's not moving. And in this time lapse here, what you will notice is from the pole star, as it slowly goes out, these stars here, they travel a short distance. The further you go out, the further they travel. Okay. And that means that in the time span that this was filmed, this star has to travel this much further in distance compared to this star has only travelled this much distance. Okay. And I've put that, replicated it on my my wheel. Find my screw to attach the camera to my Earth, which spins. And what that shows is the stars that are closest to the pole, they only have to travel a certain amount of distance, compared to a star that's further out has to travel a lot further in distance. So if you were to spin this 1/4 of a turn, you see how the outside star has to travel a lot further than the inside star. Okay. Well, I've also replicated the picture from this camera here. The Earth is stationary, looking through the rock to Polaris. This pole star doesn't go either side, up or down, is stationary in the center from this camera. The only way you could replicate something spinning is to spin the camera on the spot. So basically the camera is spinning to replicate the motion in the center, and it would have to be perfect. You'd have to engineer it perfect. Well, if you spin the Earth east, this actually does a 1 centimeter circle. So to replicate the Earth spinning, you'd basically have to spin the camera on the spot to actually keep it in line with the Polaris pole star. That's the only way you could replicate it. You cannot replicate it any way. East-west motion, the pole star does not line up. Same with if you go north-south. I've set this up to actually do a north-south rotation so it can show you what would happen if it was going north or south. It just doesn't happen. That's north-south, this is east-west. It's it just cannot happen. You'd have to spin the camera perfectly to the center of the lens to make the actual to look through the rock at the pole star. That's the only way you could do it. And even still, you'd have to invert the camera, which I'll show you right here on a piece of paper what inverting the camera means. If you have a circle, you cannot put a camera on the outside of the circle because the camera lens films in a circle like that. The only way you could do it is if you have a circle and the camera was in the center and the lens was in the center, and basically the camera spins on its axis. That's the only way you can replicate it, which proves the Earth is 100% stationary. Thanks for watching. Okay, I wanted to make a video on how the sun works. This is basically a diagram of how the outer wall, the South Pole, the North Pole, the sun travels around the South Pole, flips and goes around the North Pole. Okay, the North Pole spins clockwise, it's energy, it's a negative. The South Pole spins anti-clockwise, it's a positive. What these Nazi symbols represent, this one spins anti-clockwise, this one spins clockwise. There are two suns, one is the anti-sun, one is the sun. They attract and repel energy. Basically, like how a magnet works. Positive repels, negative attracts. That's how they work. Here is another diagram. Zoom back out a little bit. Go full screen. Spins around. The South Pole energy spins anti-clockwise, the North clockwise. The sun goes around the south, gets wider until it gets out, until it goes around the North Pole. Okay. Even the Romans knew how it worked. North Pole clockwise, South Pole anti-clockwise. Clockwise, anti-clockwise, clockwise. Anti-clockwise, clockwise. Into a circle. Into a circle. It's another older one. Into a circle. Anti-clockwise, clockwise with their Nazi symbols. Anti-clockwise, clockwise. Same again, anti-clockwise, clockwise. North and South Pole. Their world government with their Nazi symbols. Another one, moon, and that represents how the sun spins. Okay, now we'll move on to how the sun travels in Fairbanks, Alaska. The sun comes towards Alaska, looking to the south from the north. This is where the equator is. The sun actually comes to you and away from you, which means it's actually arcing away. It's not arcing around like how the flat earth model assumes to think it works. This sun is actually coming towards you and away. Speed it up a little bit. This is why they only get 3 hours of sunlight. It's because the sun is coming towards and away. And you can look at all these videos, they're on YouTube. Okay, so what that means, if we're looking at a flat earth map, zoom out from that a little bit, Alaska's at the North Pole. If you think that the sun is going around and then all of a sudden it goes towards Alaska and then away from Alaska, sorry, it would be going this way because it's it's going anti-clockwise, which means it's going from this way to that way, anti-clockwise spinning, which is what happens when it goes around the South Pole. It comes from the equator towards Alaska and then back around, towards, back around. Okay, if you think that's the only one, here's another one. Fairbanks in Alaska, different user, different post, there's many of them. People are looking at the 24-hour sun. Well, you got to look at what's happening in the winter. What way is the sun actually going? What way is it travelling? It's coming towards Alaska from the equator, from looking south, from the north. You can speed this up just a little bit. Sun comes towards and away. And disappears. So if you're in Alaska, which is in the center, the sun is going like this, towards and away, towards and away. How can it be going around in a circle and then all of a sudden it goes towards and away? That's because it's going around the South Pole, towards and away. Okay. Now we'll go to what happens in Antarctica. Well, it does opposite. It comes towards and away, but it's actually doing a clockwise circle. Coming towards, speed it up a little bit. That's because it's going around the North Pole, doing its circle. Oh, I watched it disappear, there we go. Well, here's another one from the Antarctic, comes towards, looking north at the equator, and the sun comes towards and away. Which means if you're in Antarctica pole, it's coming towards Antarctica and away from Antarctica. The same with if you're in the North Pole and it's going around Antarctica, it's coming this way towards Alaska. Okay, I wanted to make a video to show how a compass actually really works. This is a magnet. It basically attracts and repels. One side is north, one side is south. Okay, a compass will attract to whatever side of the magnet that it is attracted to. So if it's on a northern side magnet, the compass will attract to it. If it's on the southern side, it will attract to the southern side. Okay, for an example, I have drawn a line to say where north is. Okay, well, if we move the compass over to here and it's attracted to the south magnet, well, guess what? You reckon north is over here? Well, I've just changed north over there because the south is attracting to the southern magnet, the South Pole. If I spin this around to the north, it's going to attract to the north. Okay, I wanted to make a video on how this figure 8 sun and moon and all the so-called planets that they call planets the sun spins around the South Pole, it goes anti-clockwise. In your books it will tell you that it goes clockwise. I don't think this is clockwise. Well, then it goes to the South Pole and goes clockwise. This is anti-clockwise. They're looking at it from the ground up, which looks clockwise, which is really anti-clockwise from the view from above the stars. And basically what I want to show is how it actually works. I've actually pulled out a program that you can download and check for yourself. It's called Sky Maps. Well, this maps out where all the stars are, where the sun is, longitude, latitudes, the hours, basically, and you can find out exactly where everything is in the sky from the South Pole to the North Pole. Okay, the South Pole, I can map out every star that travels around, like the Southern Cross is basically here, and it goes around the South Pole like this. There's many other stars I can map out on this, and I can map them out on the North. But what I want to actually show is Australia is about here, looking towards the equator to the North Pole. The sun rises in the northwest. The sun rises over here from Australia. The moon comes from behind me in the southeast, and the moon is tracking on this line here, tracking around the South Pole. Same with Saturn, same with Pluto, same with Jupiter. The sun is tracking on the outskirts of the North Pole, and soon in the next couple of weeks you're going to watch it jump in the application. You watch it jump from the North Pole over the equator and start going around the South Pole, and you can monitor this in the application. It's called Sky Map. Another thing, if people think that it goes around the North Pole, well, it's only going around the Tropic of Cancer to the equator, and then they think the Tropic of Capricorn. Well, what you're getting is no sine wave. And what I mean by that is the sun is coming down and back up around the North Pole, down, back up. It's not coming this way. It's got to come this way and that way to get a sine wave. Yeah. I hope you understood that, and thanks for watching. Okay, I wanted to make a video on how the time zones work. Sky Map is an application that you can basically track all the stars, and it is basically designed on a flat Earth. That's how the application is designed, and then put into 3 dimensions. And what I mean by that is, this is the equator line all the way around, and what they've done is basically join them two together to make it into 3 dimensions. Basically, I've put the horizon line into the actual the program itself. I've mapped it all out. You can map it all out on the grids where the horizon lines are, and basically it shows where the sun is in certain seasons throughout the 12 months. And what I'll show you is it starts off in summertime. Summertime, the sun is going around the Tropic of Capricorn. Australia is basically here looking north, and what you get is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hours. Each one of these represents an hour. But not only that, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hours of darkness. Okay? That's because this is the horizon line. The sun goes past the horizon, you can't see the sun here. This is the 10 hours, this is the 14 hours. Well, then the sun slowly tracks its way back around until it comes autumn, which comes further out, and then you start getting 12-hour days, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hours. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 daylight, 12 darkness. Then the sun jumps the equator, usually at the equinox is what they call it, and starts going around the North Pole. Okay, and then it slowly works its way in autumn time until it gets to the Tropic of Cancer, and every time it gets closer to the center of the North Pole, what happens is you lose daylight hours because of the horizon. The lines from here to here are getting smaller. This is wintertime sun going around the Tropic of Cancer, and you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hours like what we have in the wintertime. You have 14 hours going around here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There's your 14 hours of darkness. Comes back around, coming into spring, and where the sun is at the moment is roughly in between this line and this line. It's nearly at the equator. It's about to jump the equator on the equinox on September 20. So what you'll see in the sky when it's setting west, it won't be setting west on this line, it'll be setting west on this line. So you're going to watch a big jump in the sky. This is basically how it maps out. We can go to the daylight hours. The daylight hours in the summertime in Darwin and in Hobart. Hobart has 15 hours of light. So basically what that means, Australia is here. If you go further south, this horizon line is going to go further south. So what that means is you get more time from here to here. When you go into Darwin, which is further north, you get 12 hours. We can see Darwin there. 12 hours 47 minutes. So what that means is when you go further north of Australia, the horizon line is going to come further north. So what that means is if the horizon line starts here and ends here, it means you're going to get 12 hours of sunlight through the daytime. That's basically how the time zones work on the flat Earth. Thanks for watching. Okay, I want to make another video to show why this map is wrong. They're basically saying that from Australia, the sun in the summertime is 14 hours. So if you count these, the sun is basically going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It's going to go all the way over there. So from Australia, you're going to see the sun from there all the way to there. That's 14 hours. And then they're trying to say that in winter time you only get 10 hours. Well, basically the sun is even closer, and you're only going to see it from here to here in the Tropic of Cancer. That's 10 hours. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That does not add up, does not make sense. Why would the sun, you can only see the sun close in the winter time, but you can see the sun further in the summertime. That's why this map is wrong. Okay, I wanted to make a video to show that this video is totally not reality. Jaren's challenge to the pole stars. This is not reality at all. This was made by Wolfie 6020, and he's basically saying that the pole stars are above the poles. This is totally nonsense, and I'm going to explain it why. What he's basically trying to do, he has the string line going to the roof like the stars are 1,000,000 miles away from this pole. Well, this is totally nonsense, and I'll tell you why soon. he's saying that the stars spin miles away from the actual Earth. Well, this is why. I have to take the camera out the tripod. He's basically saying that the Earth is like that. It's my pen. And his pole stars are spinning around like this. This is total baloney, and I'll explain why in a minute. He's basically saying that the reason why the Earth spins is it makes the perfect circles all the way out there. Well, no, that's not how things work in reality. Okay? And what I'm about to show you is the pole star is above the South Pole, and the stars actually spin around the pole star, and guess what? They meet up at the equator. They meet up at the equator. They are always going over Australia. Every day you can monitor them. This is how the stars go, and in the north they're exactly the same, spinning around, and they meet at the equator. Well, you get what I'm trying to draw here? Okay, the pole stars meet at the equator. They're always going over the top of Australia. They're never ever underneath Australia. So the ball is not spinning for the stars to be underneath the ball. They're always going over Australia. If you really want to check this out, you can go to Sky Map. You can go to Star Walk Sky Guide. You can go to Star Tracker. You can go to Star Chart, Sky View, Star Finder, Star Rover, Star Map. And this will explain exactly how the stars spin over Australia every single day, every single night. They do not go under Australia. They're always over the top of Australia. They're not at a pole star a million miles away like what he's explaining in this video. They meet at the equator. There's plenty of star trails that show they meet at the equator. This is spinning around the North Pole and spinning around the South Pole and meeting at the equator. They're not going to meet at the equator when they're a million miles away from the North Pole and from the South Pole. And it's due to perspective. When I'm in Australia, I'm looking 180 degrees straight up. And what I mean by 180 degrees is this is how our vision works. If you're a person here with his eye standing on the ground, okay, you're always looking 90 degrees. If you go anything under, you start off at 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees. 100, 110, 20, 30, 40, 50, 160, 170, 180 degrees from perpendicular, from the zero. So basically what that means is when you look at converging lines, if you're that person here looking, the horizon always rises to that 90 degrees. The sky always comes down to that 90 degrees. And I'm going to explain a demonstration out the backyard in a minute how that actually works. You can look at converging lines down a hallway and watch how they converge down and converge up. That's how lines work. That's how our perspective works. Now I'm about to go out the back, and what we have here is another application. Like I said, 0 degrees to 180 degrees to 90 degrees. This is how the application works. And it's called Flat Earth Detector. Okay. Now what we have here are lights. What I'll do is I'll actually plug those lights in so it makes them a bit brighter so we can see them. Alright, now the lights are on. Okay, all these lights are at the same height. They're all parallel to the ground. Okay, this line on the ground is parallel to the line at the top. We can measure it from there to there, and we can measure it from that end to the ground. Okay, well this star here, this blue one right here is, we'll call it the Southern Cross. This star all the way at the end is the pole star. Okay, and this is how you see things in perspective. Okay, the blue star. If we can get that pitch to, well, if we go straight up, you're talking 180 degrees, which is that light there. Then it goes less degrees, 170 degrees, 160 degrees, 150 degrees, 140 degrees, 130 degrees. And the further you keep looking, the perspective goes down. It keeps going down to the horizon, which would be 90 degrees. Well, when you look from the ground at 0 degrees and slowly work your way 10 degrees, 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70 degrees, 80 degrees, 90 degrees, well, that's where these lights will end up. They will end up at that horizon line. If this went for another kilometre long, this will hit the horizon. As you can see, they converge down. They converge down to the ground. Same with the ground, it converges up until they hit that horizon line. Thanks for watching. Back again, wanted to make another video. Where is your north? Well, it's a bit weird for me. Main North Road, that is basically north. That line right there, that is where the compass points north. Well, if you keep zooming this out, what I find interesting is 90 degrees off that line, east and west is this way. Yeah, isn't that odd? I mean, we can zoom back in to where we just were. North is that direction, east and west is that direction. So how do they get east and west going through this line? Where is your north? Okay, I just wanted to make a quick video on how magnetism can affect the outcome of weight. So basically here we have our weight, it's 225 grams, and what I'm going to do is put another magnet underneath, and what it will do is actually repel it up so the weight is actually less. If I turn the magnet over, the weight is actually more. It weighs 224, 225 grams. It's on that range, and by putting magnetic field underneath it, it either attracts or repels to either increase or decrease the weight of the actual iron and cobalt that's in the actual magnet. All elements are magnetic. If you research diamagnetism, there's a good video on YouTube about diamagnetism and paramagnetism. Then you have ferrite magnetism, and then you have electromagnetism, which is all the frequency bands. You're talking all the elements. I mean, certain magnets are made out of certain materials that can repel water, but they're not on the exact same frequencies, the two elements. So then therefore you're not going to get a very strong repulsion. I mean, all things are magnetic. Just a piece of steel, that's the northern end of the steel, that's the southern end of the steel, and everything's magnetic, even plastic. I mean, and rubber, you can say that it's not magnetic, but if you rub a balloon on your head, a piece of rubber on your head, it will attract to the hair that's on your head. If you get like a plastic spoon or a plastic shrink wrap, you build up with enough static, it can actually attract to your arm, and you try and pull it off and it keeps attracting to your arm. Plastic is magnetic, it's just different forms of magnetism. But electromagnetism is covering all the spectrums. And that's what else I would like to say. Alright, I wanted to make a video about how a compass works. I was told it only attracts to the northern hemisphere. So this little needle attracts to the northern hemisphere. Well, that is absolutely baloney. And their imperial science that they call imperial is not imperial. And you can prove this with a quick demonstration. This is a piece of iron. It has a north and a south end on this piece of iron. It has a polarity. The polarity means its magnetic field runs in a straight line. Well, it's actually spinning around, but it goes in that direction, the current flow within this piece of iron. And it attracts on the south side. You can actually watch the needle hit the top. We'll zoom in a little bit. And you can actually watch the needle, if it's a bit blurry, but the needle actually attracts to the top of the plastic. It actually attracts to it. And the north is hitting the bottom. See if we can get it a bit closer. It's very hard to do in a demonstration, but you can see the angle. It drops down, it magnetizes. But the way we prove that is we'll actually break the thing open. Okay, I've actually broken it apart, and the way we tell if the South Pole is, this attracts to the north, okay, it'll actually pick up the needle from the north. Now the other end of the steel will attract to the south. There is your imperial science debunked. Okay, so we can prove that the south attracts to the north end of this piece of steel, and the north attracts to the south end of the steel. So that proves the imperial science that they're testing. They're not actually testing, they're just assuming. We need to test these assumptions that they assume, because if you research how a compass works, it only attracts to the north end of the magnet, the North Pole. Well, that is totally incorrect, and I have another compass that I can test it with. It attracts to the piece of steel. The southern end attracts to it, and the northern end attracts to it. Same with this new compass, brand new, still in the packet. It attracts to it, and the other end attracts to it. That means if you're in the northern hemisphere, the north piece of the compass will attract to the North Pole. If you're in the southern hemisphere, it'll work in reverse. It means that the South Pole will be attracted to the black side of the compass. And their imperial science is not imperial. So how does gravity and all this other imperial science that they've proven to, oh yeah, it's actually true, well, this just demonstrated that their imperial science is a load of baloney. Thanks for watching. Just wanted to continue on with this demonstration. Basically, this end of the rod is the North Pole, and the north needle attracts. So while you're going around the North Pole, basically the South Pole is always changing. Not only that, the east and west line that comes off of that is actually doing a circle. It's not a straight east and west line, it's actually east and west is this way. Well, now east and west is this way. East and west is this way. East and west is this way. So east and west is always doing that circle around the North Pole. Same with when you're down in the South Pole. Well, the black needle's attracted to the South Pole. When you're going around, it's doing the opposite circle. It's doing the same thing. East and west is basically off. We point it to the south. East is that way, west is this way. You do it here. East is that way, west is that way. Do it there. East is this way, west is that way. And the same again. East is this side, west is that side. So, there you have it. Imperial science debunked. Thanks for watching. Just wanted to make a video on dimensions, especially the fourth dimension, the one that's not comprehended or understood very well. People think we live in 3 dimensions. Well, I seem to doubt that. This is basically the one dimension that everyone knows. Then we go to 2 dimensions. Then we go to 3 dimensions. Well, if you were to look in the side of this dimension, this here would be exactly the same size as this, so you'd basically be looking at a square. Is basically how you'd see that in 3 dimensions. You're looking at a 3-dimensional object on 2-dimensional paper, but if you were to look down into that wall, it would look like this. When you're talking the 4th dimension, we're talking this. The walls close in either side. That does not look like 3 dimensions to me. And the same with the roof. The roof comes down and the bottom comes up. And if you look at a hallway, this clearly explains it. The bottom is actually rising up, the top is rising down, this wall is rising into that side, and this wall is rising, deflecting back into the center of what you're actually looking at. If it was 3 dimensions, this wall would look square, this wall would look square, and it would not be reality. We're not looking in 3 dimensions, we're looking in another dimension. Why does the length, the height and the width change over depth? That's because there's 4 dimensions. You're talking the width, the height, the length, and then we're talking depth. When you're talking depth, you're talking the distance of how far away you're looking, and the length is actually changing. Same with the width, same with the height. It's all changing. And when we look at this here, this is what we're actually looking at. That's not 3 dimensions, that's 4 and 5 dimensions, because if you classify the walls closing in, that's 4th dimension, and then if you classify the roof and the floor going in, which is the roof going down, the floor coming up, the side going in and the other side coming in, you've got 4 and 5 dimensions. You've got an extra 2 more dimensions there, which is not 3-dimensional. And I'll put a video of explaining how things disappear over depth. But yeah, hopefully you understand that. It's pretty simple to understand, because if you were to look at a 5-dimensional object, this is not 3 dimensions. It's actually, we're including depth in this. When you have 3-dimensional object with no depth, yeah, it'll look three-dimensional. But you put depth in that, this actually gets smaller than this. And I'll put my other video connected to this video, so I hope you enjoy. Okay, I just wanted to make a demonstration on another dimension that is not forthcoming, what we do not know about, that we do not understand. And we have height, width and length, but we also have depth. And what I mean by depth is the ball has length, it has height and it has width. It could be a square, you could have it as length, height and width, okay, which is your three dimensions. But then you have depth, which is distance away from that object. And the further the distance you go away from that object, the smaller that object becomes. And if I could zoom out another, this is only 6 meters from the ball. If I could zoom another 10 times that, that ball would go to basically a pinhead and you wouldn't actually see it. It's why we can't see New Zealand from Australia, and it's why planes disappear in the sky. You can look at a plane in the sky and it will disappear in the blue sky. That's because you have another dimension, which is the fourth dimension. It's something that science has not even looked at. We just think we live in 3 dimensions. Well, we live in more than 3 dimensions. Thanks for watching.
Alright, this is just a little time-lapse video, I think. Zern, what's up, man? Flatlines, Manny, Michael Jordan. This is, I'm not sure what, it's just a little time-lapse video. I probably shouldn't have put this one in there. Yeah, I know, this is 2015 shit. I know, man, but we gotta keep putting it out because there's a lot of newbies coming in, man. A lot of newbies. And we gotta keep it going, man. We have to keep this shit going.
Just wanted to make a video to show how these stars are going from north to south. As we can see which way the compass is pointing. It's a brand new compass in its packet. Okay. That's where I was filming last night. That's my tripod right there. And those stars are going from north to south. Straight over that shed. North to south. East to west is a totally different direction than those stars. West is over there, that's where the sun is setting, but the stars are going in that direction. How can that be possible? Also, there's no magnets or anything like that. That's the direction. North-south. Thanks for watching. Okay, I wanted to make a video why the AE, the Gleason's map, the UN map is all totally incorrect. It has everything to do with the sun's location, which way it rises and sets. And the sun rises in the southeast. It goes north of South Australia, where I am, and then goes back around and sets southwest. So it's actually doing this arc. It's not doing an arc around behind South Australia and then coming back towards the north. It's going this way. This is why the AE map is incorrect. The same with the Gleason's map. The sun is rising from the southeast. It heads north of South Australia and then sets southwest. So it's actually doing this arc. It's not going from the southeast behind Australia and then setting southwest. It's actually coming north then back to southwest from southeast. So it's doing this. I have some videos of the sun setting, the sun where it is to the north. I don't have the southeast sunrise at the moment, but I do have it going from north to southwest. Thanks for watching.
Right, wanted to make a video to show why an auto level has to have a short range. It can't go over a long distance, and it's due to the magnification of how things work. For an example, I've lined up this circle which is in the center and it's level to the camera. So if I take this camera another 10 meters behind me and zoom into this hole, it should all line up, which means it's level. And basically what's happening is the auto level is basically coming backwards at a distance. So it's looking at the lighthouse at a distance, and what happens, I'll zoom back into this so it lines up to the circle hole. Turn it a little bit. Okay, so the circle's back lined up. What's happening is the zoom on the magnification on the auto level is basically like it's only half way to the lighthouse. It's not all the way to the lighthouse, which is going to give you that correct level. So basically, by bringing, if you were halfway to that lighthouse out in the ocean, you'd probably get a correct level of what you're getting. It will be very close, but because you're double that length, which is all the way back here, if you watch what actually happens to the ruler, it's actually going down, and that's basically what's happening. You go to 32 times zoom, which is basically here, it looks like the horizon is actually below what it should be, where if you kept zooming in, it will line up to the circle hole and the correct level. That's why it's designed for short range leveling instrument, so you can magnify like you're actually at that location to measure it. As soon as you start getting further away, it's like you're halfway to that lighthouse, and then the ruler starts going down. The further you go out, the further away you get from it. Yeah, thanks for watching. Okay, I wanted to make a video of scale of the sun to the earth and how it does not work. 1 centimetre would equal 1 million kilometres. So therefore the Sun would be 1.39 centimetres, which would equal 1.39 million kilometres. The distance to the Sun would be 149 centimetres, which would equal 149 million kilometres. Well, the Earth would be 0.012 of a centimetre, which would equal 12,000 kilometres, because 1 millimetre equals 100,000 kilometres. So therefore, 1/10 of a millimetre would equal 10,000 kilometres. Okay, so there is our Sun. Then we go all the way down to 149 centimetres, which would equal 149 million kilometres. Well, this is actually a little bit bigger than the Earth, because this is about 2 millimetres. The Earth is 0.012 of a centimetre. So it's basically almost 1/10 of a millimetre, which is basically a dot. But we'll compare this thing here, which is a little bit bigger, so we can see the darkness of shadow. Okay, what I have up there is a spotlight. It has a filament basically about 3 centimetres long by not even half a millimetre thickness, okay, which is around 15 square millimetres. So it's not even 1/4 of that Sun size. And it's only 150 watts, so it's putting in very little light. The Sun is much brighter than this thing. Okay, so what we'll do is we'll turn the Sun on. It's actually around about the same distance. Okay, well, let's have a look at the shadow. Let's move this out the way. Let's have a look at the shadow from the Sun. Okay, so this is the shadow that you get from your little Earth. Well, what about the stars that are further away than the Sun? This is all lit up. All around the Earth is all lit up. You'd see daylight this side of the Earth and daylight that side of the Earth. What about the stars? What, the stars are in this little shadow here? Yeah, right. Far out. I didn't know that. I thought they were 4 quadrillion kilometres away. Well, there's your shadow, man. Work that out. Thanks for watching. Okay, here's a challenge for all globe earthers. I'd like to see how this is done and how you show your geometry on how this works. Okay, this is in 4.5 hours time from when we are right at this present moment. This is where the Sun's going to be over South Africa. It also lights up South America, and it also lights up half of Australia, almost to South Australia. It's still lit up. How does this work on your globe? Okay. How does this, the Sun is basically here over South Africa. How does it light up half of South America to Australia, half of Australia? Get your globe models and demonstrate how this works. Is it because the Sun is over the South Pole and is lighting up these 3 areas? Well, what about the Northern Hemisphere? How does this work on your globe? That's what I'd like to know. There's time and date. Tells me half of Australia's lit up, half of South America's lit up, and the Sun is over South Africa. Show us your videos. Bring on the demonstration. Thanks for watching. Okay, I have another challenge for the globe earthers. The other one was probably a bit easy because it's a ball earth experiment. But this one's a flat earth experiment. And how do you explain it on your ball? What we've got here, this here is the axis of the Earth, okay, the tilt. This is the north and the south magnetic field, which is 23 degrees, 23.4 degrees from the South Pole and 23.4
0.4 degrees to the North Pole, which will give us our magnetic readings. Okay, well, I'm 34 degrees south. Okay, my compass is parallel to the level ground that I'm standing on. It's not pointing 50 degrees, which is what that angle there is, if it was coming from a north magnetic field under the ground. Okay, if we line that up, we're talking 50 degrees to that magnetic field. It's not doing that. The magnetic field is parallel to the level land that I'm standing on. It's coming from a magnetic field, what, up in the sky? How do you explain this? A crystal clear demonstration how you can prove that this magnetic field is coming from the north. It's not coming from the center of the earth, because the magnetic field will point to the center of the earth. It's coming from a location this direction. Like with my compass, the magnetic field will follow the compass. Okay, it's following it. If I go under the table, you see what happens? Okay, we lift it up and we lift it down. You see what happens when it goes up and down? The magnetic field is coming from the parallel flat plane. It's not coming from the beneath us at the North Pole, 50 degrees, because the compass would be saying so. Okay? You understand that? It's coming from a location parallel to the compass the needle. If it was coming from underneath, the magnetic field goes down. You understand that? Pretty simple to explain and demonstrate. How do you demonstrate that you see it's touching the plastic? Okay? From a magnetic field under the table, which points it down. You understand that? Common sense. I'd like to know exactly how this is explained in the ball model, because I don't understand it. I understand it on a flat plane, but I do not understand it on a ball model. Thanks for watching. Okay, I wanted to measure the luminums of the sun, because in my demonstration the luminums are around 500 to 600. Out under the veranda it's roughly 3,000, 4,000 luminums in the shade under my veranda. Okay, there's the direct sunlight. What we'll do is we'll stick this thing in the direct sunlight, okay, to try and get a maximum reading of luminums. Okay, it'll give us you can see here where it says 200,000. Okay, we got 223,000 luminums, our maximum. Well, the light that I'm using is only 500 luminums, as I'll show in the demonstration. I wanted to make another video about scale. That's basically the sun, 1.39 centimeters in diameter. 1 centimeter equals 1,000,000 kilometers. The sun would be 1.39 centimeters. The distance from the sun to the earth is 149 centimeters, which equals 149 million kilometers. And the earth would be 0.012 of a centimeter, 12,000 kilometers. Okay, well, what I want to show is the luminums that the light produces. The sun produces around 220,000 luminums. I've got a tape measure, 150 centimeter mark. We come all the way down here, which is 149 centimeters, which equals 149 kilometers. Well, what we'll do is we'll measure the luminums at the moment. The luminums are around 70, 80 luminums. Okay, now what I'll do, that's just the light in the room, is I'll turn on the spotlight. Now let's check the luminums. You're talking 360 luminums. Well, the sun is 220,000.
if I go closer to the light, the closer I get to the light, the brighter the light will get. The luminums will increase and increase and increase because it's getting brighter and brighter. So the Earth is basically sitting in light somewhere. What are we at the moment? 95,000. Okay, that's sort of roughly 20 centimetres from the light. But what we're measuring is 149 centimetres, which is around 300-400 luminums to cause the shadows. Well, what we've got here is that 2 millimetre bit of black plastic with its shadow. There's a 1 millimetre little, it's about 3 millimetres, that black thing. There's 1 millimetre. There's our 0.012 of a millimetre, and look at the shadow of the Earth. Well, not only that, the pole star is this direction, 4,000 kilometres, and the pole star is down 4,000 kilometres because it's at a right angle to the light. If you work out 433 light years, it works out to 4.5 quadrillion kilometres. Well, if you convert that to centimetres, it works out to 4,500 kilometres in this scale. So, yeah, try and work that out. How do you see the pole stars when that's the darkness behind the ball? The North Pole and the South Pole, the atmosphere would be a light. It would be blue sky, because the sun doesn't just shine on the ball, it shines on the atmosphere as well. So you'd have blue sky either side, either end of the top and bottom. Doesn't make sense. Does not make sense. Not only that, the shadow that the Earth is producing is that small. This is where all the stars are in the night time. Doesn't make sense. Anyway, thanks for watching. Okay, I wanted to make a video to show how the sun disappears on a flat plane. It's no different to how these lines disappear to the same point. This line here joins up to the same point as this line here. So imagine a sun that is up miles and coming down. What it's doing is it's coming down to this point. This is where it's the vanishing point. That's how perspective works. These parallel lines, these are all parallel, don't forget. Look at the angles that they change. Well, when the sun is up in the sky, up higher at the same length or the same height as what it is length, well then it will come down on a 45-degree angle and it will appear the same size as it goes down and travels to the vanishing point. Even though it's going in a straight line, it looks at the same size, it doesn't change size, but it disappears to the vanishing point. It's not like this line here goes to a certain area and then this line here goes to a further point that you can see further down the field. It comes to the same point as what this line comes to. And the higher this goes up, it just angles sharper. That's all it does. It's very simple and easy to demonstrate. Anyway, thanks for watching. Okay, I was told that the sun doesn't change size. Well, I have two videos here of the sun setting in the southwest from Australia. And if we play it to where I zoom in, to the exact moment to where my camera doesn't zoom in anymore, and measure the sun size is 6 centimeters. Okay, well, I have another video that also measures the sun size. Okay, this is a different video. This is from up on my roof, not from the ground. Okay, we'll go full zoom. That's where my maximum zoom is. Now we'll measure the circumference, the diameter of the sun. That says 5 centimeters. That was actually 4.8 centimeters. So how can it go from 6 centimeters, we see where 6 centimeters is, to 5 centimeters if the sun doesn't change size? This needs to be studied a bit more.
I think we need to get our solar filters out, measure the morning sun, the afternoon sun, and the sunset with solar filters and measure it. Go maximum zoom, so then that way they're all equal. I know if I zoom into a 8 ball from the exact same distance and then zoom into that 8 ball from the exact same distance, well then therefore the measurements will be exactly the same on both video footage. So yeah, this needs to be studied more. Thanks for watching. Okay, I wanted to make a video about the axis tilt, okay, and the magnetic field, and basically I'm in Australia, okay, sort of like so, Australia. Well, if I look at Polaris, okay, this is the pole star, the magnetic field is to the right of Cygnus Octantis. Well, if I look at Polaris pole star, the magnetic field is to the right. Well, if you go to the opposite side of the globe, see how I've got another piece of paper underneath which mirrors this image? Well, if I spin the ball around to the other side, you people in America now wonder why the magnetic field is still on the right hand side of Polaris. Okay, it should be on the left hand side. The magnetic field should be to the left. People in South America, okay, and America, the magnetic field should be to the left of Polaris. It shouldn't be to the right of Polaris. Now ask yourself what's going on. I've checked this out on Google Earth, and yes, the magnetic field north should be left of Polaris. I've contacted someone in America, in Disneyland, and the magnetic north is to the right of Polaris. Ask yourself this question: you on the same side as me? How can the magnetic north be on the same side? Okay, the magnetic north is to the right of Polaris. It's on the same side as Australia. Anyway, thanks for watching. Okay, how to measure the angle of perspective. What you do is you measure the height of what the object you're measuring is. Okay, then what you want to do is measure the angle to whatever you're measuring to, and you want to measure this distance. So you have the height distance, the angle, and the distance of this blue line, and then you can work out from the height to the distance of this blue line, and you'll get your angle of perspective, and I'll demonstrate that outside. Okay, how to measure the angle of perspective, how this beam looks and is travelling down. Okay, when you put this on the ground, you'll see that beam is actually angling towards the ground. You might think it's parallel to the ground. That end is actually higher than the end here. Okay, so the way we do this is we measure the height. Okay, we'll get that on the ground, touching the ground, and we measure the height, which is 204 centimeters, if you can see that. And that's basically to the bottom of that beam, 204, 2 meters and 4 centimeters. Now, that's to the base of the beam. Well, this light is actually a little bit higher than the base of this beam. Okay. Now what we want to do is measure the angle of the beam. Put it on that side of the beam,
and you can actually see the arrow. See the arrow? Well, that's pointing that direction. The actual drain is up that end, so it's actually higher up this end than it is up that end by 0.2, 0.3 of a degree. So it actually runs downhill that way. Now what we want to do is measure the angle which is roughly 14, 15 degrees. Roughly 14 and a bit, 15 degrees will go. Okay, so we've got 15 degrees. Now what we want to do is measure this string line. On that string line there is a black dot. Okay, I have a black mark on that string line. We want to measure the length of this string line. Okay, we have the tape measure. Okay, there's my black mark. Stretch it as much as we can without it coming off the thing on the end, which is 7750. 7750. We had 15 degrees, and it was 2040 was the height, the length, and the degrees. Okay, now we'll go inside and we'll draw up those parameters, and this will show you the angle of perspective. Okay, now I want to draw the angle of perspective. What we have, okay, there you can see that it's all correctly measured. .90 degrees. Okay. 15 degrees. Okay. There's your 90 degree mark, there's your 15 degree mark. Now we want to measure, first of all, I've scaled it down, okay, 7750 divided by 4 is 1937, and 2040 divided by 4 is 510. Okay, so what we've got here is .510. $19.37. Okay, so this is on the 15 degree mark. Let's get this correct. Okay. I've gone 1940, a little bit higher. It's actually 19.37, but that's 19.4. Okay, now if we draw a line from our 510 mark to our 19.4 mark and draw a line, straight through there, you will see your angle of perspective. Okay. Now if we measure, okay, get that straight over the top of it, so you can see that's on that point mark. You see how it's lost 2 millimeters? That's because that is the angle of perspective. And the further you go from something, the angle changes and the angle of perspective changes. Same with the higher something goes, the angle of perspective changes. And it's measurable. It's just proven that it's measurable. Thanks for watching. Okay, I wanted to make a video to show the shape of the Earth. Is it a simulation? What is a simulation? And basically I'll just try and explain how a simulation works. For an example, this guy here, if you were seeing through his eyes through the simulation and he was walking in the simulation, he's not actually moving. The ground is moving underneath him. Okay, you can see that he's always in front of the screen by a meter and the ground is always moving. And that's how a simulation works, is that the ground moves, not the person. So if I was this person in the simulation, I would feel like I'm actually moving. That's me walking rather than the ground moving. It's the same when you have a car or a plane. This is in a plane. I'm watching a simulation of a plane. Okay, well, the ground is actually moving, not the plane itself. The ground is coming underneath the plane. But if I was in this simulation, I would think I'm actually moving. I'd feel like I'm actually flying. It's just how a simulation works. It's the same with a car. If I'm in a car, for an example, watching the simulation from outside the simulation, the car isn't moving, the ground is moving. Well, this is a real life footage of someone driving a car. Well, the thing is, if I was in this car driving it, I would feel like I'm driving it due to the senses that I have and how I experience things inside the simulation. It's like programming this guy in the car to have feelings and senses and emotions and all the... He feels like he's actually real, where in fact he's just programmed to feel like he's real. You could program this guy that's in this car to build the car, build an aeroplane, build anything. You can program him to do that. And he will think that he's invented a car and built a car, and the thing is, he's just been programmed to build that car. The same with watching this. If I was playing this as a game, I would just be playing it as a game and thinking that I'm driving the car, but I'm not in fact actually moving anywhere. The ground is moving underneath me, but because I'm inside that simulation, it feels like it's real. It feels like you're moving along the ground. Sorry, the battery went flat. But yeah, even in this simulation, if this guy runs 1,000,000 miles in this simulation, it's nothing but a calculation. He hasn't run anywhere. He can run as far as he likes. He's still in the same location. The ground is moving. If this was me in the simulation, I'd feel like I've ran 1,000,000 miles, but in theory, the ground has moved 1,000,000 miles. And that's basically how the Earth works. That's my theory on how the Earth works. Even this guy in the simulation, he's in the same location as this guy. He's basically exactly the same. He's just moving relative to me in his simulation. He's in the same simulation. But yeah, even though you can drive 1,000,000 miles. It's just a calculation in the simulation. But yeah, anyway, I'll get on with showing you how the Earth, my theory on how the Earth works in a simulation. Okay, this is how simulation works. You're on the outside of the simulation, I'm on the inside of the simulation. And basically, when I walk around, does it feel like your camera screen is moving? Or does it look like the ground is moving within the camera screen? The screen that you're watching, it just looks like everything is moving within the screen. Your computer screen isn't moving. It's only that I'm in the simulation and I feel the sensors and the motions and every little electrical signal to feel, and I think that I'm actually moving, when in reality you're just watching me through a computer screen. That's how a simulation works. Okay, this is how I believe the Earth works in a simulation. There's my my model of Earth. But basically, everyone is along this center line, which is your north to south, which is negative to positive, which is the electronic field within Earth. This is where all the signals come in to Earth for the simulation. For an example, if I'm in Australia, well, for an example, the sun. When the sun moves around the Earth is moving under the sun. So basically the sun, this is at the equinox. So the sun itself has an angle from the sun to the north to the south pole. That's where the light exceeds its limit. It can't light up any further. When the Earth is spinning, or when the sun is actually going around the Earth seems like it is moving under the sun. Okay, it's the same with if I want to go to Australia. I'm in Australia. Okay, this is me in Australia, and I want to go to America. I'm basically traveling around the Earth. The ground is moving underneath me. Okay, and now I'm in America, but my parents are still in Australia relative to me. Well, the people in Australia are in the same location in Australia, and I'm here relative to them. If you understand that, in a simulation, that's how it can work, because we're all down this same line. This same line can make you think that you're on a ball. But this is basically demonstrating how the equinox works. The sun is in the center. For an example, if you have two of these, this is your equinox line. This is the summer in the south. This is the summer in the north. Okay, and if you spin these down that equinox line, that's why the sun is going down that straight line. And that's why if you spin these around together and they all join up, what happens is you make the exact same map as what the Google Maps makes. It makes our exact map. Which is this map. That's what it actually makes. You have the North and South Pole. Okay. How the sun actually works for seasons. The sun and the moon actually goes from the Tropic of Capricorn, Cancer, all the way up to Tropic of Capricorn, and comes all the way back within 1 month. And what happens is when this is spinning around, that moon is slowly going up. This is the sun spinning around the 23-degree latitude, okay, and it's lining up with South America
it goes over Australia, it goes over Africa, goes over South America, back around to Australia. And the same with how I showed in my time zones. Oh. What was that under? But that's basically how it works. And when the sun and the moon, they do the same speed, and when that goes up here, basically what is happening, here is my other diagram. Pen underneath. When I'm in Australia, okay, the sun, you can see my sun, the little, let's see if I can zoom in on it, the little yellow ball, okay. Australia is down the magnetic line, but what's happening relative to me is the sun looks like it's moving around. Okay, you understand that? Another thing is temperatures. When the sun is over Australia, you have cold this side. Basically, the sun shines. Oh, I'll zoom that back out so you can see. When the sun is basically over 23 degrees south, the sun shines to the other side of Antarctica, which is this circle line, and it shines to this starting line. So if I spin this around, the sun is always going to be shining to here and to here, all over Earth. Okay, that nail's not hammered in properly. But what that does is the temperature up in the north is freezing cold, okay, because the sun is so far away from the north. It's over the top of 23 degrees south, so everything in the south is hot, apart from the distance from the sun to Antarctica. That's why you have this cold area around here, and the same with why you have the cold area around here. Well, when it changes seasons, this sun comes slowly towards the equinox, and then you'll find you'll get a hot area over the equinox. It starts to get colder here, and it's starting to warm up here. By the time this sun moves to here, now you have a hot temperature here, and you have a colder temperature here. This explains the temperatures. A sun that's 93 million miles away on a ball, for an example, this is the equator line. A sun over 23 degrees, okay, is going to warm up this area at around 30 degrees. The further you go this way, 20 degrees, 10 degrees, freezing. Then when this sun goes back over the equator, you're getting average 30 degrees here, back to 20, back to 10, 20, 10. By the time the sun's back over 23 degrees north, then you're getting your temperatures again back up to 30, sometimes 40 degrees, because the sun is over your head. It's not a million miles away. And when the sun is over the equator and it shines to the South Pole and to the North Pole, like how the diagram is, what do you think that represents? This is your south, this is your north, and the sun is at the equator. What does that look like? Nothing conspiracy at all. But anyway, but yeah, that basically shows how my equinox works. It's the same with
the stars, if you're in Australia, the stars are spinning around on the top. So basically, if you point your telescope with the polar axis to the center, it's doing exactly what it is on the bottom of a ball. It's tracking the circles around the pole star. And another thing is perspective. I've actually made a video demonstrating that you can actually measure the angle of perspective, and that's basically how you see things. Things actually bend down. It's a proven fact. You can actually measure it, mathematically measure the angle of perspective. When things get further away from you, they go down. And that's how things works, like how a hallway works. But that's my demonstration on how a flat earth can work in a computer simulation. Thanks for watching.
Okay, we have the morning sun, and I want to measure the light intensity of this sun, and it's basically no clouds in the sky, so we can get a direct reading from the sun. Okay, put the phone in the sun, we're getting around 170 maximum luminance from the sun at the moment. I'll just show you. 178,000. Well, we'll see what it is at lunchtime. Usually when a light comes closer to you, it gets more brighter, more intense. I'll demonstrate that later. Okay, it's been about close to an hour since our last measurement. We'll put the luminance into the sunlight to see what maximum luminance we can get. Okay. Now we're increased to 194. So it's increasing in light intensity by it coming closer to me. We'll test it again soon. Okay, it's been about an hour since I've last tested it. There's a little bit of cloud cover in the sky. Okay, this is what our reading is at the moment, 114,000, so we'll stick it in the direct sunlight and see what our maximum luminance. Okay, now we're at 220,000 from 180,000 from 160,000, so it's increasing. Well, I had to abandon the test because it's just too much cloud cover to even see the sun at the moment. But for anyone interested, I'd advise you to test the light intensity of the sun from morning to night and see what happens in brightness and measurements. Thanks for watching. Okay, I want to make a video about how a camera works. A camera has a lens, it works exactly like the eye, but it actually goes to a screen, okay? Just like this camera, it has a screen, a digital screen from the camera lens. So the camera basically gets all the optics and puts it into a screen, okay? Just like this camera. This camera goes to a screen. Well, your eyes are around 550 megapixels to around 600 megapixel cameras. Do they go to a screen outside the box that we live in? Like this camera, a security camera. It electromagnetically Wi-Fi's the signal to a screen, okay? So basically, when you're looking around, are your eyes electromagnetically sending a signal to a screen outside the box that we live in? Are you being watched? Just go and think about that before you insult people and abuse people, and just wonder, are you being watched? Thanks for watching. Okay, what are sensors? Why is it that when I'm in Australia, I always sense the south is behind me when I'm looking north? But if the Earth spins, why is it that I always sense the north is this way, in this direction. I never feel like I'm on the other side of Antarctica. I never ever feel that. I never feel that in my senses. I never feel that the north is pointing that way. The north is always pointing in that direction with my senses. Same with if you're in the northern hemisphere. The south is always in that direction. Okay? And when you spin around the pole star, why is it that south never feels like it's in that direction? Why does it feel like it's always in this direction? Yeah, just think about that. Have a good one. Okay, I just wanted to show you how to test my theory there, Wolfie. The pole star is roughly here in the center and all the stars are spinning around the center. Well, these two stars here, if we measure the size, the length of these two stars, okay, we'll get that one on there, is roughly 4 centimeters between those two stars. Okay, now what we'll do is we'll play the video. These stars are basically in line with the pole star over here. These stars aren't even above the pole star, and I'll show you what happens with the angle, because you can measure the angle from this star to this star. Okay, now here we have these two stars coming around. You see how they're going around the pole star. Pole star is roughly over here somewhere. And what we'll do is we'll measure these when they get below the pole star and see if they're still at 4 centimeters. Okay. Oh, gone a little bit too far. We'll go back a touch. These are the two stars right here. Well, now you're talking 3 centimeters, okay, because they're further away. That's what happens with perspective. Things get smaller as they travel further, and the gap between the two is much smaller. Thanks for watching. Okay, I just want to make a quick video about SpaceX and its launch and amateur videos. So I'll just try and upload as many amateur videos so people can click the links and watch all the amateur video footage and determine for yourself if it's real or not. Thanks for watching. What I want to show is how the stars do the 2 circles. Okay, the sun does it also. Here is the sun. The sun does the circle and then it flips the equator and goes to the other side. But the stars also spin around the southern pole star and spin around the northern pole star. And I'll explain how they do that. And also the stars that go through the equator, like the Halley's Comet and etc., they go around here in the outside, okay, and then come through the equator from the outside. That's why you see them in so many years, and basically that's how the stars work. They only meet on one side of the equator, which is in the center. The stars go around the outside. You get the main stars that go around the pole and your planets and etc., but things like Halley's Comet and different comets, they come from the outside through the equator and through the outside through the center. You understand that? But anyway, I'll let you watch the video. Well, the easiest way to prove we are not on a spinning ball is the time-lapse photography. People say that the flat earthers are in the dark ages. Well, we're in 2018 and we can use the technology of today, not technology of 300 BC. And time-lapse photography says it all. If the earth was spinning, this is the equator. These stars should be touching these stars, okay? It's making 2 circles like this. That is basically what it's doing. The stars on this side are not touching the stars on this side, which is the equator line and the equator line. So basically what it means is you have 2 separate circles of stars, if the stars were spinning, well, the ball was spinning to make the stars go around the ball, they'd all be like this, in a vertical line, spinning. Okay, and not only that, these stars are doing the small circle and then the bigger circle and bigger circles and bigger circles until they meet at the equator all the way around the ball. So the stars on the southern end are touching the stars on the northern end all the way around the ball, if you understand what I'm saying. If you don't comprehend what I'm saying, it means you are not understanding basically how and what I'm explaining here. And when you look at all time-lapse photography, the stars on this end are not touching the stars on this end, which means that they're not meeting at the equator. They're only meeting at the equator in one area, which is two separate circles of stars. Same again, you have the southern stars and the northern stars. Well, these stars all should be meeting at the equator. These stars are going to the north, these stars are going to the south, like how I show here. Every section of this circle on the outside should be touching every section of the circle on this side, like how the ball is in the middle of the stars. These stars at the equator are touching these stars at the equator. Not only that, when you're at the equator, the stars travel in this direction, which is this arc, and the stars are traveling in this arc. They're not traveling in straight lines around the ball, which means that they're traveling like this around the actual, well, the ball would be spinning, but the lines would be going in straight lines, not arcing from the equator to the equator and away from the equator to the equator and away from the equator. So that basically proves that we are not on a spinning ball, because you'd be getting lines of stars all the way from the equator to the pole. You're finding that the pole is here and the stars are spinning around the pole and meet at the equator at one edge. Okay, all of them. They're arcing this way and arcing this way. You don't get that if you're on a ball spinning. Arcing both ways, arcing this way, arcing that way. Okay, you sort of understand what I'm saying? If you don't understand it, try and comprehend it, and then you'll be like, oh fuck, yeah, that's exactly correct. Arcing this way, arcing that way. If you're on a ball, the lines would be all parallel and spinning because the ball is spinning. These lines would be, every single one would be parallel. These stars would be making small circles, and the further it gets closer to the equator would be making bigger circles to make the stars in a circled time lapse as it goes down and as it goes down. But this isn't reality. So again, they arc in and arc in to the equator and meet at one edge like that. Anyway, thanks for watching. I want to make a video how YouTube are suppressing me, basically. Suppressing comments on my page. Okay, if we go to this star trail video, I'll show you. 57 views, it says there's 8 comments, but there's only actually 1 comment on the page. If we go up to comments, people that have commented on the page. Okay. Not only that, they're slowing down my streaming. I can click on any other link and do a speed test and it's fine, but see now how we've got another comment here by Abu Ismail. Okay, there's more comments there. But then if we go to another comment that was posted on this same video of star trails by Flat Earth Dude. Okay, same video, 57 views, star trails, exactly the same. But now Ismail's comment is removed, you see. We've got no fanfare, Flat Earth Dude. But then if we go back to Ismail's comment, which is up here, Flat Earth Dude's comment will be removed. Okay.
See, there's no flat earth dudes comment. So there's 8 comments there, but if we go to my home page, we'll go back to the star trails. You watch the video, it just doesn't play. It downloads, but it doesn't play. And pause, play, it just doesn't work. It sits there. And then it just comes up with, yeah, see, no fanfare, 8 comments. Dude's post isn't there, and Ismail isn't there. And now we're getting playback doesn't begin shortly. Okay, well now we'll go to run a speed test. I'll show you my speed is fine. Nothing wrong with my speed. That's because they're playing funny buggers with me. Anyway, thanks for watching. Oh, 666. Have a good one. Okay, I made a video about this picture a while ago, and what people seem to fail to understand is which is spinning, the Earth or the stars. Okay, and what we'll do is we'll do a simple demonstration to prove, and you determine for yourself. Don't let me determine what you think. Okay, you determine for yourself what do you think is spinning. Okay, stick this in my tripod. We'll zoom it into that picture a little bit, because what I've got is I've got a background of stars behind the. It's either the stars are spinning, okay, in that hole of the rock, or it's the Earth is spinning around like this to keep that pole star in the center, if you understand that, because it has to spin on the axis to keep that pole star center. And if you think the Earth is spinning around like that, well, yeah, that's basically the axle. Okay, so the axis, so basically the Earth is spinning on this axis of the camera. Or is it the stars spinning in the background and the Earth is stationary? Thanks for watching. Okay, today is March 20th from South Australia, and basically if we set the compass needle on due north and due south without any magnetic declination, the sun is setting directly west on the compass without any magnetic declination. But if we move it, so we got, my other compass says it's 8 degrees declination, which is a compass on my phone. I'll show that in a second. But if we move it to 8 degrees west is where that tree is, where the light post is, and the sun is magnetically west. Okay, we'll line that line up and go straight up from there, especially going to that light post. That's if you put declination in it. Or if we don't put declination in it and put it so the compass needle is on north, well then yes, the sun sets directly west. I wanted to make a quick demonstration on what happens. This is the pole star, okay? And I'm always looking in this same direction towards the south, okay? If the Earth was spinning, that drone would be actually looking in the opposite direction in the sky by the time I went to the other side of the Earth. And I'd be looking in the opposite direction of the sky, because that's what happens when you spin around a ball. When you don't spin around the ball, you're always looking from the same side, okay? We're looking in the totally opposite direction to what I started. Same with if I keep going around, you go around the pole star. The pole star doesn't stay in one location and stars spin around it. That's the problem with sticking a camera on a ball. You have no senses. You don't know what's actually really going on, especially in the mind. People can't imagine things, imagine what happens, how it looks. Imagination is where you take photographs in your mind so you can see and work out how things work. Every invention was worked out via imagination. They imagined it first. They could see it in their mind. That's how inventions get invented. Okay? By sticking a camera on a ball, there's no senses, there's no imagination what's actually going on. I'm always looking at the pole star like I'm standing here right now. It never changes, it never moves. Okay? If the Earth moved, the pole star moves in the sky around, and you go around the pole star. Doesn't matter if I'm at 80 degree latitude, 30 degree latitude, or at the equator. The pole star, you go around. You go around the pole star because the pole star is above the center of that pivot point, okay? And you would continuously go around that pole star. It doesn't happen. It's illogical. It's not reality. The pole star is stationary and the stars spin around the pole star, not you spin around the pole star, okay? The pole star is always like that, always stationary in the sky. You don't move. You don't go under the ball and look at the pole star upside down from the other perspective. No one can imagine that because they don't know how to imagine. That's why they put fluoride in your water, so you can't imagine, you can't see from the mind, which is basically like taking photographs from your mind. When you can take photographs from your mind, you'll realize we don't live on a ball. Thanks for watching.
Alright Wolfie, I thought I'd make the video. Well, for starters, it's they say it's 10,144 kilometres to Cape Town from Adelaide. So if we were using a litre a kilometre, we would need at least around 13,000 litres. If we were using 2 litres a kilometre, we'd want around 26,000 litres of fuel just to make the journey. What people see, my thought on how relativity works is you are always constantly still. The only reason when you walk, all you're feeling is electrical signals to make you think that you're actually moving. You think that the Earth is stationary and you're moving on the Earth like this. Well, that's where I see it differently. I feel it like how in the song says it, you feel the Earth move from under your feet. So basically you are stationary. You might be walking with your feet, or you're flying with a plane, or driving in your car, but the pen is stationary and the Earth moves under your feet. So you're basically staying in the same position. It's just that you're feeling electrical signals like in your movement of your legs, and you're feeling those signals to think that you're actually moving. Same with a jet engine. You're feeling the acceleration, which is just electrical signals that your body determines. You're hearing sound waves, which is electrical signals. That's all it is electrical signals. North is negative, south is positive. And determining on which direction you're traveling determines on the pull or the push, like how a magnetic field works. Same with west to east. West is negative, east is positive, because that's the direction energy flows. Energy flows from north to south.
You look at all the water currents on the Earth, they flow from north to the southern hemisphere. That's how all currents, electric currents, water currents, flow on the plane. Same with from west to east in the equator. But for my map, like I was saying, you think that you're moving from here out. But if I hold this pen still, okay, we'll get it so we're in Australia and we are down this magnetic field line, okay, which is from north to south. We're basically stationary here. In South Australia, I would travel directly west, because this is south, this is north. Directly west is, I'd actually go a little bit northwest, because if I went too far southwest, I'd actually miss Cape Town and fly past it. So if I make sure we're going a little bit northwest, then therefore we'll make landfall. So if I keep this pen here and I start moving to the northwest, what do you think happens? The pen's not moving. It's just that we found Cape Town and we stayed in the exact same position. We haven't moved. The earth moved under our feet. That's because the motion of our legs interpret from the electrical signals, think that we're actually moving, when theoretically we're actually stationary and everything else is moving. It's like when you play a video game or a simulator, you can see in the plane simulator, if you're outside the simulator watching, the plane's not moving. The ground's moving from underneath their feet. And when you're in that simulation, if you're in that game that you're watching from outside the screen, you'd feel like you're flying, you feel like you're moving, but you're watching it from outside the screen, nothing's moving. The people in the simulator aren't moving, the actual ground's moving. It's the same with in this life. If you go and jump into a simulator, you think you're flying the plane, the simulator's moving and you're getting all the motions and all of that, the electrical signals. But in reality, you're sitting in a cabin and the cabin is moving and the ground is moving, but it's simulating what you feel in this reality. And I just explained it exactly how, not only that, if we keep the pen there and we keep going, we'll actually go to South America. And if we keep going, we'll go all the way back around the world. You can only see, in reality, less than this circle down that line. We're seeing about 5,000 kilometers in this little circle. Okay? This little circle represents about 5,000 kilometers of the Earth, which is nowhere near that. And I just explained how you can go around the world by a simulation. It's very simple, it's very easy. You can build a computer game based on this, which would replicate Earth as a flat Earth, and it's in 5 dimensions. I've got to make another video on how we live in 5 dimensions, but that's another thing. That's basic how it can work. We're always down this line. We're always from the positive to the negative, the magnetic field. Plain and simple. It can work. I could build this in a computer program and design it exactly like this, and it will work. It's not rocket science, man. Anyway, thanks for watching. Wolfie, I'm down on the flat plane at the soccer club here. Okay, and I've got my drone in the sky, which is, see where that tower is? Well, the drone is at 30 degrees from where I am at the moment. Okay, you see the drone there? Okay. If I get out my application, put it on the drone, okay, it's at 30 degrees. You can see that? Now what we'll do is we'll walk closer towards the drone, okay? And the closer I get, the angle to that drone is getting steeper. and steeper and steeper. Even though I'm walking on a flat ground, I don't need to be on a ball, okay? Now the angle to that drone, you're looking at nearly 45 degrees. 40 degrees. I'll just walk 10 meters closer to that drone. Now what I'll do is I'll keep walking closer to that drone, okay? And eventually, I'll be 90 degrees straight below that drone. Do you understand that? Even though I'm walking on a flat plane, it's flat. The angle is changing due to distance. Now the drone is at 60 degrees. Okay? And the further I keep walking and keep going, eventually that drone is going to be almost 90 degrees on the drone. About 80 degrees to that drone. We keep going forward. Now the drone, a bit forward more. Now the drone is exactly 90 degrees. Okay? 90 degrees straight above me. Okay? Even though I've walked across a flat plane, it's just changed from 30 degrees to 90 degrees. That's how angles change over distance. You don't need a ball to change an angle. Okay? Thanks for watching. Okay, Wolfie. The biggest problem we have here is you think that we live in 3 dimensions. We don't live in 3 dimensions. We live in a warp dimension, okay, which is the warping with inside the square. The square is basically this with the sphere inside the square, okay, but that is the dimension that we live in, which is the same as this here, which is why we see clouds. If you're standing here, you see clouds that are perfectly level, okay, that actually bend and arc to the horizon. That's because space warps, okay? When you're in your plane and you fly to this altitude, these clouds will actually bend up and they will appear level to you when you get to this altitude, okay? Same with trigonometry. Like I said, you can be standing here and you measure 50 kilometers to the horizon, okay? These clouds are at 0 degrees. The problem is they're at 0 feet. The biggest problem is they're actually at 10,000 feet. It's because space warps. You can actually measure this. You go get a drone, okay? You measure, put the drone at a certain height. Actually, put it at this height here. What actually happens, because space warps, the drone will actually appear here. So the drone, in reality, is at about 25, 30 degrees. But what you will actually see is because it warps, the drone will be at around 15 degrees, okay? So when you're measuring it here, at the drone up here, it's actually going to give you a measurement of around 15 degrees. And when you measure the trigonometry from the distance of this here, the drone is actually up here. And you can measure this, you can actually do this. Get the measurements and you'll see the trigonometry doesn't work in 3 dimensions. It works on a 2-dimensional piece of paper working out a triangle, yeah. But in 3 dimensions, because space warps, this is what happens. That's why clouds appear on the horizon. It's not because you're living in 3 dimensions and they're going around curvature of the Earth. When you get in your plane and you get to this height, all those clouds are level. It's the same with when you put your eye on the ground and look at the ground is level. When you actually go up in the sky, the ground is actually starting to bend up. That's because space warps. Thanks for watching. Okay, I wanted to make a video about dimensions. Okay, most people think we live in three-dimensional space like this. Okay, with your X, your Y, and your Z. Okay, so it makes this sort of grid pattern in cubes. Okay, which is three-dimensional like this. Well, this has more than 3 dimensions. Okay, if you want to say it's three-dimensional and this line is the line that you're looking down and the cubes are all so forth, but when you turn, the dimensions change. Okay, and if I was to make 360 of these squares, 360 dimensions on the horizontal plane, I'm actually looking at a circle. Okay, because all of these squares will actually make a circle if you do 360 of them. Not only that, you have it on the vertical, so you're actually 360 squares makes another circle. So you're actually living in a dimension of a sphere, okay, which is like this. This is how you see things. You see things in a circle around you. Not only that, the dimension is on the vertical, exactly the same. So it makes a circle, a sphere. That's the dimension that we live in, which is, if you want to add all the dimensions up, there's 720 dimensions. That's my calculation, because I can put 360 degrees in a circle. You could even double that. You could make it so there's 720 degrees in a circle, because if you put a degree in between every degree, then it would become 720 degrees in a circle. But we live in a minimum of 720 dimensions, plus time and space, which is another 2 dimensions in itself. But anyway, thanks for watching. Well, Wolfie, you told me that I was wrong because you've used this screenshot. It's 3.7 degrees to the horizon. The thing is, your camera's tilted 1.1 degrees. But then we'll go over to this shot here. Do you see what that is there? It's 2.8 degrees and it's set on the horizon. So we can't be using the screenshots to determine what it actually is. Here's another screenshot at 4 degrees on the horizon. Okay, and then we've got a 3 degrees that's up here. Okay, another 2.8 on the horizon. Another 3 degrees on the horizon. 4 degrees on the horizon. Or another 2.9 on the horizon. But if we go through it, okay, we'll come from the start. It's at 2.2. Okay, this is where you pan over, because we'll go through from screenshot to screenshot. Okay, we're nearly level there. Okay, and then you pan down. Okay, 0.1 degree now. Okay, now we just hit 2 degree. This seems steady to me. 2.8, 2.9, it's sitting at a roughly 3 degrees. That's your 4 degrees. Oh. You see how it's all shaky. Let's pause that. That's 4.4 degree. But if you go through each one, look how shaky, and it's at 4 degrees. I don't think your application is very correct for one, because shows here 2.8 degrees to the horizon. Same with this one here, 3.1, and it was steady from the start. 3 degree, 2.9, 2.8. It's very steady at that spot. 2.6, 2.2, 2.1. But anyway, I just thought I'd show you that. Thanks for watching. Okay, geometry and what is it? Okay, I know when I measure geometry, I measure from the center of the circle and I measure 360 degrees from that center of the protractor, and I'll get my 90 degrees or 360 degrees. Well, when I move the protractor to over here, is that relevant to the measurements over here? Of course not, because you've moved the protractor. It's the same with how we measure the ball. We're basically moving the protractor. We think that we're moving the protractor all the way around the friggin' ball. That's not how you take measurements of geometry. Geometry is taken from one measurement, and that is you. You're the one that takes that measurement. Like this. Regardless if it's a ball earth or a flat earth, we can measure those 10 degrees on a flat plane. The thing is, that flat plane comes to us. We always measure from the person on the ball. Okay, so we'll set the protractor up to 0 degrees. Okay, now if we go 10 degrees around the ball is going under us, and we are still measuring from that same person, that same location of where the person is measuring from. Just because you're at 10 degrees, it doesn't mean you move the protractor 10 degrees and then measure and then move the protractor again and then move the protractor and move the protractor. You're always measuring from the person. So if I measure another 10 degrees, well, now we're at 30 degrees. Well, 30 degrees off of that is up here. Go again to 40 degrees. 40 degrees is up here. 50 degrees is up here. We're always measuring from the person. You don't move the protractor to do geometry. Geometry is always measured from the center to 360 degrees. And I'm sure a lot of people understand that, and this is why we assume it's a ball. Thanks for watching. Back to Geometry 101 again. Okay, what we have there is basically this. You're basically saying all those parallel lines are the same as this line here that goes to the pole star. Okay, and we're at the equator, and it's in line with the horizon line on the equator. Well, when I go 10 degrees, you're basically saying that the Earth is tilted down 10 degrees, and the Earth is tilted down 20 degrees, and 30 degrees, and 40 degrees, and 50 degrees, and 60 degrees. You're measuring the angle of the Earth. You're not actually measuring the angle of the star. And what I mean by that is if you're at 10 degrees, the ground is actually level still where you're measuring from. When you're at 20 degrees, the ground is level where you're at. 30 degrees, the ground is level. And notice what's happening with the star. The star is coming closer to you. Eventually will be 90 degrees above your head, but the ground is level. That's because you've walked to it. When you walk that way, the ground is always level, but the star keeps rising and rising and rising. What you're misrepresenting is you're measuring the angle of the Earth going 10 degrees around, and that's not the case. Even like this, This is not right geometry. Even though I'm measuring 10 degrees, 20 degrees, 30 degrees, I'm not measuring from the same location, like the point of where you measure 360 degrees. I'm measuring from different locations. Okay, it's more like this. You're at this, where you're measuring from, the 10 degrees comes closer to you. Okay, so the star goes up, the 10 degrees goes even closer, so you're at 20 degrees and 30 degrees and 40 and 50 and 60 and so on until you get under the pole star, which is 90 degrees. It's all to do with measuring. You don't measure geometry in different locations. That's not how you measure geometry. Anyway, thanks for watching. Okay, I wanted to make a video to show why they believe that it is a ball rather than a flat earth. Is because they're doing geometry of the sky and determining the shape of the earth. And what I mean by that is, if you're at the equator, the pole star, okay, is almost 0 degrees on the horizon. So if we get our ruler and we walk 10 degrees, we're walking, but we're measuring from the same spot. We're measuring from here, from the person, and now we have a 10 degree line. If we walk another, it's like the earth is bending as you're walking, but theoretically it's the stars coming closer towards you, and that's 20 degrees. We keep going. 30 degrees, 40, 50, 60. So they're basically basing the shape of the earth off the angle to the pole star. That's how they get this curvature, but there is no curvature. It's just that the earth is flat, and when the pole star comes closer towards you, because you're walking closer to it, it's changing the angle, which is giving you the determination of the shape of the earth, which is a load of garbage. But anyway, that's why you think it's a ball. Thanks for watching. Okay, I made a video the other week about angles change over distance. Okay, well, if we were to do the geometry of my angles changed over distance, which is the angles of what I measured from 70 meters away, the angle was 30 degrees. So if we start from underneath the drone, well, when I go to 80 degrees away from that drone, the drone actually moves 80 degrees away from me. Same with 70 degrees. Same with 60 degrees. And that drone is getting further and further away from me because I'm on a flat surface. But if we were to do the geometry the same as the ball geometry, well, there's the curvature of the flat park that I was flying at, because 30, 40, 50, 60, it's going up in increments of degrees even though it's flat. That's ball earth logic. Have a good one. Alright, I wanted to make a video about geometry and how it's being measured. It's basically being measured like, here is a person, and you think this person travels 100 kilometers over to here, okay? But the problem is, you think it's two people. It's in two spots. It's 100 kilometers apart. No, this person hasn't traveled anywhere. This person is always staying in the same location. Regardless if you think it's a ball earth or a flat earth, when this person moves 10 degrees towards the pole star is actually coming towards him. Okay? You want to keep going 20 degrees, 30 degrees, but the star is up here coming over. What you're not understanding is you think you're two people measuring at different distances, the person is never at a different distance. It's always the same person. The person never moves. He is always in his body, okay, and always in the same location. Everything moves around you. You're not moving around it. That's the problem. Why, whether you think it's a flat Earth and you're moving up and down the flat Earth like this, or you're walking around a ball, you're always maintaining upright. You're always on the top of the ball. The ball is spinning like this and you're taking measurements. You're not going around the ball taking measurements. You understand what I'm saying? If you don't, try and work it out. Okay, let's talk about a bit of flat Earth geometry. Okay, some people say geometry on flat Earth can't happen. Well, it's pretty simple really. For an example, the pole star is on the horizon, you're at the equator. Okay, you start walking 1,111 kilometers towards that pole star, the pole star comes up 10 degrees. You're still filming, taking that measurement from you, the same location. So by moving 100 kilometers this way, 1,100 kilometers this way, that pole star goes up 10 degrees. And if you do the same thing again, the pole star goes up 20 degrees. Same again, you do the 1,111 kilometers and the pole star goes up due to those kilometers. You understand that? Do it again, another 1,100, the pole star goes up and up until you're under that pole star. Okay, I've drawn a few pictures to demonstrate how this actually works. When you're at the equator, all the lines are parallel over your head, coming straight over your head at the equator and up and around due to perspective. That's another thing. Then we'll go to 10 degrees. The pole stars come up 10 degrees because we've moved 1,100 kilometers. Okay, and what happens is the angle changes of the stars rotating around the pole star. Okay, now we're at 30 degrees. The angle is starting to change on that pole star. Now we're at 40 degrees. The angle's still changing. We're still measuring from me. The angle's changing again, up to 50, 40, 50, 60, 70, 80, 90. Now we're under the pole star. Those stars have angled and changed as we've walked towards that pole star. 9,999 kilometers. But what's just happened is everything's moved around us, and the other part, 90 degrees, was always 90 degrees. You understand that? We just walked down a whole flat Earth and we went to 90 degrees. The problem where you're going wrong is you're measuring from here to here, but it's really you here. You think you're this long. No. The sky is moving around you, if you understand that, and it's very simply explained. That's because when you move, you don't move. Everything moves around you. That's why the sky rolls. Anyway, thanks for watching. Okay, back with Jazz with flat Earth geometry. Okay, for an example, how does the equatorial mount work from where you are, your location? Okay, well, if the pole star's at the equator, because all these stars are spinning 90 degrees to this line here, to the pole star. Well then therefore you line up your equatorial mount to the pole star and the stars spin 10 degrees either side of that pole star in a circle, and 10 degrees this way, 10 degrees that way. Same with this star. You can track this star because it's doing the same circle. Same with this star. And then when we move to 10 degrees, sorry, this is 30 degrees. This is 10 degrees. Well, the stars start to angle up because you're getting closer to that pole star. And the same again. You line up the equatorial mount to the pole star and this degree has changed. You see that? Then we move to 40 degrees. As we get closer to that pole star is actually getting closer to us. Same again. That's why you can track stars in the sky on a... Well, do you have curvature? Because that's where you're measuring from. You're not measuring from anything else but using distance. And that distance that changes in the sky is how you get all these measurements. Because you're measuring from yourself. So that's how an equatorial mount works on a flat Earth. Very simple. Thanks for watching. Okay, back with Flat Earth Jazz. Bit of geometry. How does the equinox work? Okay. Well, you know this picture, where are we? We're straight under the pole star, so on the equinox, which direction would the sun be spinning? Sun would be spinning along this circle around here and around here, wouldn't you? Because it's the equinox. Okay, well, because we're at the under the pole star, let's go back to the equator and see which angle the sun is on the equinox. Okay, the angle of the sun is starting to tilt up as we slowly make our way back to the equator through here. That's because we're moving back to the equator. Everything is slowly moving back. Now we're back at the equator on the equinox. And guess what? It's rising in the east and setting in the west due to perspective. It's actually going around the pole when you're under the pole, yeah, but when you walk back, it's actually, the perspective is bending. You understand that? That's how the sun works on the equinox. Thanks for watching. Okay, welcome to Jazla's Geometry. People think we live in 3 dimensions, X, Y and Z. No, we live in 12 dimensions. People think all the blocks are the same size. 3 dimensions, every block is the same. No, that's not correct. I'll show you why. Okay. If I join all this up so it makes a block, everyone will think that all these lengths are the same length. No. For an example, from here to here is 9 centimeters. Okay, 9 centimeters. Well, guess what? From here to here is 9 centimeters, but it's only 5.5 centimeters. So 5 centimeters equals 9 centimeters. Okay. We could change that to 10 centimeters if we really like. Same with this length. This length is 6 centimeters. This length is 6 centimeters. We can change that. 6 centimeters equals 9 centimeters. Centimeters. Or we can change that to 8 centimeters. Even though it's a box. That's how you bend space. Same with this line here. This is 9 centimeters. And it is actually, shit, it's 9 centimeters. Not bad for guesswork. This is the same. 9 centimeters. Well, guess what? This 2.3 centimeters equals 9 centimeters. This equals 9 centimeters, and it is 5.5. Do you understand and see where I'm going with this? That is 12-dimensional space. When you're doing geometry in 12-dimensional space and doing 3D geometry, no wonder why you think it's a ball. Do you know why the road looks like that? And not like that? It's because we live in 12 dimensions, not 3 dimensions. Like I was saying to Wolfie, if the circumference is 40,000 kilometers and the diameter is 20,000 kilometers, what is pi? Ah, well, from here to here is 10,000 kilometers. It actually works out to 15 centimeters. Okay, but it's actually 10,000 kilometers. From here to here is 10,000 kilometers. You understand that? That's how you bend space. Do you see a footprint in this? I see a footprint. Looks like a flower. Yeah. Anyway, thanks for watching. Alright, welcome to Jaz's geometry. Well, this is genometry. Okay, this is the sun in the morning on the horizon, and your level plane is basically like this. And the Earth slowly turns and the plane angle is now like this, and then the plane angle keeps angling and angling and angling as it goes around, and you're on the other side of the ball. So basically you start on this side of the ball and you're basically going around. By the time you get to the other side of the ball, you're 20,000 kilometers away from this apparent sun. Well, do you know what the angular size would be for 20,000 kilometers at something this size in the sky? Yeah. Or does it work like this? You're standing on a flat plane and the sun does a perfect circle, 15 degrees around you. Is that how it works? Because that's how it works for me. I'm always standing upright. I'm not going upside down on a ball like this. Okay? So, for an example, if the sun was out this direction while it's rising, I'm on this side of the ball. You understand that? By the time I move 20,000 kilometers to the other side, this sun angular size would change significantly. Okay? And not only that, if I'm standing on my level flat ground and the pole star at the south and the north, and I walk to the pole star, what do you think that I'm going to be facing this way? Or do you think the pole stars will start moving over your head like my diagrams show in my other diagrams? That's because for every 1 meter you move, you think space is in square blocks, okay? For every 1 meter you move, this sky up here moves 1.5 meters. Okay, so every meter you move down here, the sky moves 1.5 meters up there. That's why it can move 15,000 kilometers on the sky, on the horizon, the pole star. Okay, when I walk 10,000 kilometers, this moves 15, but it's actually the same distance as this. So the pole star is actually moving from here to here. That's how space bends. But anyway, here's another great example of ball earth geometry. You can be standing at the equator, okay? This is the north and south pole in the center, so you're looking down the axis. You can be standing at the equator and you do a 40,000 kilometer circle around the ball, yet your telescope's lined up with this. Yeah, that's geometry. Then we have about 20 pole stars on the side of the ball. We don't know which is the pole star, and the pole star spins around over here, but then when we move 20,000 kilometers over here, the pole star's spinning over here and spinning over here. You understand that? That's not geometry. Perspective. Perspective bends down and bends down. Something that's further away from you will go down. The pole star here does not bend up. You understand that? The perspective doesn't bend up, so the pole star is here while you're standing at the friggin' equator. Great geometry. Not only that, it does it up the other end too. Oh, trigonometry. Trigonometry. Yeah. Yeah. This is the sun. The sun, yeah. Two parallel lines. How far is two parallel lines? Work that out. Well, that's 93 billion miles. Well, then we got the pole star that's two parallel lines. We'll just call that, I don't know, a few trillion. Great geometry. That's how good the ball earth geometry is. Definitely not precise. Exactly like my little demonstration of the flat earth that turns into you think it's a ball. Yeah. Thanks for watching. Okay, welcome to Jazz's geometry. Alright. I did try and explain it very simple. We get comments like this. Please do show the model and don't leave out the 60 nautical miles per degree this time. Well, I didn't leave out that. I deliberately left that out as an IQ test. And I'll explain right now with my comment. Let me just find it on my phone. I actually wrote it twice. There's another one. Please do show the model and don't leave out the 60. It's written twice. Well, we'll go to this and we'll look at the reply that I replied to it. Mate, 111 kilometers, 60 nautical miles for 1 degree is there. It's like an IQ test. Go to the picture at 10 degrees. Where is the equator? Now go to the picture at 20 degrees. Where is the 10 degrees and the equator? Keep going until you get 90 degrees. Well, I'll show you a simple explanation. I know you don't understand 12 dimensions in 2 dimensions, so I'll do it a bit simpler. But here's the pole star at 10 degrees, okay? For a simple explanation, this is not the equator, okay? This is 10 degrees. So where is the equator? Well, the equator is here, because the star has travelled 1,111 kilometres up, which is 10 degrees, okay? And you understand that? So I've actually, when I've walked closer to the star's come back, gone up 1,100 kilometres, so then therefore the equator actually goes this way. You understand that? It's not, I'm at the equator and I walk to 10 degrees. Well, it's similar to that, but the equator is actually going behind you because you're walking forward. You understand that? Very simple terms. Okay. We have our north, south, east and west. Well, I'm going to show you a simple two-dimensional diagram, okay, and we'll use the longitude line. Okay, we all know what a line is. It's very simple to see. This is the longitude line from side on. Okay, this is the equator, this is the pole. Now if we walk to 10 degrees, okay, well, let's start with arc seconds. If we walk 1 arc second, which is 30 meters, the equator goes this way 30 meters, this pole star comes up 1 arc second. Now, if we go 1 arc minute, is approximately 1.8 kilometers. So the pole star comes up to here. The equator goes back to 1.8 kilometers. Now we'll go 60 arc minutes, which is 111 kilometers, which is 1 degree. It would probably be roughly here. Okay, because this is 10 degrees. When we go 1,111 kilometers, the equator is here. This is 10 degrees, and the pole star has moved 1,111 kilometers. Now we'll go to 20 degrees. It can be measured in arc seconds. Okay, we go to 20 degrees. Well, as we're walking forward, everything is going backwards, so the equator is here. 10 degrees is here. 20 degrees is here. You understand that? 30 degrees. Slowly walking forward, everything is going backwards because this is actually getting closer to you. When you get to 90 degrees, the equator is right here. This is 90 degrees underneath you because everything from here is moving because the pole star will eventually become 90 degrees. You understand that? Very simple explanation to prove we do not live on a ball, because if you go put 10 degrees of curvature for every 10 degrees of latitude, you're going to be all out of whack. Now if you understand the equator is here, okay, this is 90 degrees and this is 90 degrees. This pole star is actually 80 degrees. If we put a pole star here, now what you have is a set of tits with 2 nipples. Yeah. Thanks for watching, guys. Have a good one. Alright, welcome to Jazla's Geometry. What we got here is we've got the Tropic of Capricorn, the Equator, the Tropic of Cancer. Where I am at 34 degrees south latitude, in the summertime, the sun rises 120 degrees to the east. It also sets 240 degrees to the west. The zenith angle is 80 degrees. I'd like to see this, the geometry of this done, to show me how these sunrises match up with this line. Anyway, thanks for watching. Okay, welcome to Jazla's geometry. I gave the ball earthers a challenge. They obviously didn't want to take up the challenge, so I'll show you the challenge. Okay. What we've got here is, we can give you the sun angles. Okay, that's fair enough. We can get all the zenith angles from every latitude. But what about the sunrise angles? Okay. For an example, I've got 3 different locations on the flat plane. This is South Australia. Okay. Here's the ecliptic. Okay. 23 degrees. Okay. This is my sun angle at zenith, which matches the ecliptic. But what about the sunrise angle at 240 degrees and 120 degrees east when it rises and 240 degrees when it sets? Well, this is the angle. This doesn't line up with this angle. Okay? Because this is where sunrise is and sunset is. This is where zenith is. This is the dark side. Okay? This is on the 23rd of December. You can go and check these angles on timeanddate.com. Okay, and I'm 34 degrees south latitude. Okay, the angles don't line up. Well, now we'll go to Washington DC. Okay, on the 23rd of December, 38 degrees north latitude. Okay, the zenith angle matches the 23 degrees tilt that we so-called have, which is a load of garbage. But then what about the sunrise and sunset angles? It rises 120 degrees east, sets 240 degrees west. Well, off of this latitude line, okay, 240 degrees is this line here. Does this match up with these lines here? No, it doesn't. Okay, you got to put the sunrise and sunset angles in, because if you don't put the sunrise and sunset angles in, you're not doing geometry. You're doing genometry. You understand that? Here's another one. This is December 23rd, Caloundra, Queensland, which is 26 degrees south latitude. Okay. The zenith angle matches the ecliptic, but the sunrise angle is 117 degrees. The sunset angle is 243, if I remember correctly, from timeanddate.com. Okay, do these two angles, the sunrise and sunset angles, match the zenith angle? Do you understand that? You can go put this into your 3D geometry programs and you'll see it's all a hogwash. Anyway, thanks for watching. Okay, welcome to Jazla's geometry. What we got here is magnetic declination, something I didn't put in my sun angles, but even if you put it in, things get way out of whack. And this proves that the Earth does not spin. Okay, yes, fair enough. The magnetic south is to the right of the geomagnetic south. Okay. From South Australia at 30 degrees, it's 10 degrees to the right of the geomagnetic south. But when the ball spins around 180 degrees, okay, if you're looking back at it, the magnetic south is on the opposite side of the pole star, even though it's still on the same side. Looking at it back from the other side of the ball, it's on this side of the Earth. So therefore, east and west changes (10 degrees). East and west changes. You understand that? Goes from west to west, east to east, by the ball spinning around. The magnetic declination goes from one side, spins around the ball, and it's on this side of the ball. It proves the ball does not spin. It proves you do not live on a ball. You understand that? Very simple. Einstein said you can't work out a way to detect if the Earth spins. Well, that's proof in the pudding. The Earth does not spin because the magnetic field is always on this side. The east does not move 20 degrees by the ball spinning around, and west does not move 20 degrees by the ball spinning around because I have a 10-degree declination. You understand that? Very simple, basic, provable. You can demonstrate this easily. Anyway, thanks for watching. Okay, welcome to Jazla's Geometry. What I wanted to explain about how this all works. Okay, people say, oh, they're just lines, these are lines. No, these are actually, each line, okay, represents a circle. Okay, all the stars, like the Southern Cross, travels around the circle. Here's the pole star, the north end, the southern end. It doesn't matter if you're at the South Pole or the North Pole. Okay, this is how the stars, the geometry of the sky is actually designed. Okay, so for every one of these lines, it represents one of these rings. The smaller the line, okay, the smaller the ring. Okay, it's like how you turn a hula hoop on its side. So basically this here, these circles are turned on their side. That's the side angle that you're looking at. Okay, in the summertime, in the South Pole, the sun gets to here, the Tropic of Capricorn, okay, to this ring. Then it slowly makes its way down. As it slowly spins, the angle in the sky will be 20 degrees at the Tropic of Capricorn, okay, at the South Pole. And then it will slowly make its way, keep spinning around and round and round until it gets to the equator, okay, the equinox. The equinox is basically spinning around on the horizon. Okay, for an example, I'm at 30 degrees latitude, or 34 degrees precisely. Okay, well, 80 degrees is the Tropic of Capricorn, 40 degrees is the Tropic of Cancer, 60 degrees is the equator. Okay, for every latitude that you're at, for an example, if you're at 40 degrees latitude, the equinox sun angle will be 50 degrees because it adds up to 90. So if you're at 10 degrees latitude, okay, the equinox will be, 80 degrees at 10 degrees latitude. Okay, if the pole star is at 10 degrees because it adds up to 90. Same with at 30 degrees, it adds up to 90. 40 degrees, it's at 50. 60, it's at 40. They're the angles to the equinox sun. Well, 80 degrees is the Tropic of Capricorn. It slowly spins around. Like I said, these lines are circles. The sun spins around the Tropic of Capricorn, okay? Then eventually it jumps the equator and starts spinning around to the Tropic of Cancer. And then it works its way back out again, jumps the equator, spins around to the Tropic of Capricorn. Okay, you understand that? The moon does that as well. Okay, so do the stars, the so-called planets. The stars spin around in circles like that. Okay, so for an example, if it's the sun is at the Tropic of Cancer, we're at 40 degrees. Well, in this diagram, the sun is below the horizon spinning around the North Pole. That's why you don't see it in the southern hemisphere. But when the sun hits the equinox, the sun, okay, is on the horizon. Then it slowly spins around and slowly makes its way higher and higher and higher in the sky. And if you look at my other diagrams, you'll see how you can go from the the South Pole or the North Pole all the way to the equator and how all of this bends in the sky. Okay, and you'll get a better understanding of how this actually all works. Okay, for an example, the Tropic of Capricorn, the sun is rising rising at 120 degrees east and setting 240 degrees west from where I am. Okay, that's how it looks in the sky. Okay, this angle is exact angle of the sun that from the horizon to where it gets to the zenith to where it gets to the horizon again. Okay, same with at the equinox. It rises and sets east-west, exactly where you are, east and west. East and west. Well, the sun goes up, okay, from east, directly 90 degrees, up, 60-degree angle, comes back down to the west, exactly 270 degrees, okay, and then when it slowly makes its way to the Tropic of Capricorn, then the angles start to change again. They go into the northwest and northeast. You understand that? It's very simple. Anyway, I hope you understood a lot more of this and you get a basic understanding of how it works on a flat earth. Thanks for watching. Alright, welcome to Jazla's channel. We have a little probability problem here. If we have a van and we have a drone, okay, and this drone is traveling with the van at 60 kilometers an hour, and you wanted to fly the drone in the same motion as what you're traveling versus the same motion of the opposite motion of what you're traveling, is the drone going to hit the back of the van faster than it will hit the front of the van if it's in the center while you're traveling in that motion? Just have a think about it. Anyway, thanks for watching. Okay, welcome to Jazla's Geometry. What we had today, we had a concave earther, because that's what it is, it's a con. Okay, I can debunk it within a minute, that's why I never even looked at it again. And he says, concave earth, no mate, the earth is a flat sphere. You effing moron, I dare you to debate me. Well, there's nothing to debate, mate. I'll debunk it within a minute. Minute 30, I'll debunk it. Okay? This is your so-called concave Earth's sphere in 2 dimensions, okay? This is the equator that comes over and around, and your universe is inside the sphere, okay? And the pole star is above the South Pole and above the North Pole. Well, the thing is, when you're standing at the equator, okay, the pole stars are 180 degrees from each other, which means 180 degrees. Okay, this is 180 degrees. They're not 40 degrees from each other, they're 180 degrees, which means the pole star is on the horizon and on the horizon. Okay, you understand that? That's why concave Earth is a con. Anyway, thanks for watching. Alright, welcome to Jazla's channel. Just want to show how time works. Okay, we have the north, we have the south, we have the underworld. Okay, how this works is the north spins clockwise, okay, the south spins anti-clockwise. And what that means is the north, the energy comes out of the north and goes in the south. Okay, so it basically goes from the north to the south to underground, through and back. That's basically how the energy flows. Okay. what it means is comes from the north up, which is a 9. Okay, it's a 3 in the middle and a 6 in the south. So it's basically 9, 3, 6. This vortex goes down, all the energy, this vortex comes out. Okay, what I've done is basically sent a photon down here, and rather than it spinning this way, the vortex, the very small vortex, it's now spinning the opposite way. And what that means is the energy is flowing back up from the south. Okay, so now you have a positive and a positive. Okay, the sun, this is time basically staying in, going forward, backwards. The sun is why time goes forward slowly, because it goes through you until you die. Okay, now what basically it means is this is a green light, this is the orange light, this is the red light. Okay, so what it will do is turn this into a 9, okay, this into a 9, and this into a 9, okay, because what it's doing is this spins from the outside in, this spins from the inside out. By the energy coming up from the south, it's spinning from the inside out clockwise. Okay, what it's doing is it's creating resistance, and what you'll find if you research the Schumann resonance, you'll find that the heartbeat of Earth is actually increasing, the energy coming out of Earth, because the spin of the white hole is actually bringing the energy up back out of the South Pole. Okay, it's also coming out of the North Pole. We are on the cross in the center. Okay, and what's going to happen is when this spins, this was done in 2014 when the Schumann resonance has been from 1950s when we've been recording it to 2014, then all of a sudden it started to increase, because the photon that was sent to the core is actually bringing the energy back out. Okay, and it's slowly winding its way up. This one goes this way, remember? Okay, well, this one is going this way. When this spiral, okay, hits this spiral going this way and this way, what do you think happens here on the cross? Anyway, a good song to listen to is what we're going to do is turn this to a green light, this to a green light, and this to a green light. And what I've done is I've ripped a hole in the fabric of time and space, because energy is actually space compressed, moving. So if you actually compress space and bend it, you can actually move it. Okay, and that's basically how space and time works. If you listen to a song called Bliss and Esso, My Life, then you understand exactly what I've just said. Anyway, thanks for watching. Okay, welcome to Jazla's Magic. What we got here is how you make time out of empty space, nothing. Okay. These two white squares are exactly the same size, but what you do is you bend the space, so you pressurize this space compartment. And this is on an atomic scale, so this dot represents this much time, because if I pop a hole right here, what happens is this pressurization releases into this nothingness. Okay, and what happens is this starts to fill up and pressurize. Okay. Now what happens if you have one of these, but it's infinite? Okay. And you have a valve coming in. Okay. This is how electricity works. So this infinite valve of space, empty nothingness, can keep filling up every positive atom, and it Fibonacci spirals down to this side. So it basically, because you've got the hole here, it's going in this direction. Okay. And this is how the whole Earth works, because time has been going in a line. Okay. Like this. Because if you keep filling up this to go to here, to go to here, to go to here, what happens is it's going in one direction and it's expanding. Well, how do you turn back time? You pop another hole in here and stop the flow here. Or you put you close the valve. So what happens is all the space from here starts going the opposite way, because it's blowing into another air pocket, which means time is going into here, to here, and to here. Okay, but you can constantly keep feeding this one, so it keeps going that way and keeps going that way. How do you connect time? By one of these. This has to connect to this side, and it has to connect to this side to make time go in a loop, so it keeps going. This is how electricity travels. The atoms within this circle all travel this way, every single piece of atom, which means the universe is actually getting smaller and smaller as it's slowly going. It's like running a computer forward, but then turning it off and running it on capacitance. The actual computer is actually running backwards, not forwards. And if you keep feeding that capacitor, then therefore the computer will actually run backwards, is basically what's happening. Because it's turning off, and that's what we're in. We're in a world where it's turned off. The energy is draining from us. We're supposed to be batteries, and the energy is coming from the core up, so it charges us like a mobile phone charges, because the polarity is coming back up. All the energy is coming back. So it's pressurizing. Anyway, thanks for watching. Okay, I want to make a quick video of how an equatorial mount can work on a flat plane. Okay, this is the southern pole star from the equator. Okay, and it's 10,000 kilometers from this star to the equator, where I am standing in this center. I'm always in the center. I can never get to the equator, because when I move to the equator, the stars 30, 40, 50, 60, the stars actually go over the top. Now an equatorial mount will work is because the polar alignment, that this angle here from where you're always standing is centered to the center, and these circles are actually spinning around this pivot point, this axis. That is why you can see the stars, depending on if you're at the equator or 10 degrees, that pole star is moving towards you. Okay, and those stars are spinning around that pivot point until you get to under the pole star. You understand that? That is why the sun itself at the equator is spinning around this bottom circle, and then 10 degrees higher and up to 20 degrees in summertime in the south. Okay, but when you walk back to the equator, notice the pole star is actually moving away from you back, because you're traveling to this side of the screen. The pole star is going away from you until it gets to the horizon. Therefore now you're at the equator. If I went to the South Pole, the ground doesn't move like this. The angle of the ground stays flat like this, and the pole star slowly becomes above my head. It's all to do with perspective. But anyway, that was a quick demonstration on how a equatorial mount can work on a flat plane from the northern hemisphere to the southern hemisphere. Okay, the ground is staying flat. You understand that? And it's due to distance. It's the same distance from the star to where I'm standing, from the north to the south. Anyway, thanks for watching. Okay, I wanted to make another video. I get a lot of ball earthers saying that's not how it is, and this is how it is. This is sky maps. If you actually look into sky maps, doesn't matter what star program you use, this is how the sky works. Okay, when you're at the equator, when the sun, this is the southern pole, this is east, this is north, this is west. Okay, when you're at the equator, when it's winter time in the south, the sun is in the north, 20 degrees. See, every one of these is degrees, 20 degrees, 30 degrees, 40 degrees from the center. The reason why an equatorial mount works is because it works to the center. You are the center. Okay, that's the only reason why it works, is because it is the center of the sphere. You're always in the center. Okay, you understand that? When I'm at, for an example, this you can use all over Earth. Okay, the pole, okay, that is at the equator. When we go 10 degrees, 20 degrees, 30 degrees, 34 degrees, okay, because if you count these 10 increments, this pole star is 34 degrees to the center of the other side, which is the northern side. Okay, so it's in the center of the sphere, and that's why the equatorial mount will work on a flat plane or a ball. It doesn't matter, it's because it's going to the center. Now if we look at sun angles, okay, if you look on this white sheet of paper, this is east. Well, then the next one is 100 degrees, 110 degrees, and 120 degrees. So the sun rises in the summertime 120 degrees, okay, over my head, and then it sets 240 degrees on the other side. Okay, in the wintertime, it's rising nearly 60 degrees. Okay, 60 degrees and setting 300 degrees. Okay, so it doesn't matter where you put this, anywhere on the Earth, this is how it works. And you can travel from the equator all the way to the South Pole. This is the North Pole, all the way back to the North Pole. You understand that? And when I'm under the North Pole, the sun in the summertime in the north is spinning around this loop, okay, at its highest point. That's why you're getting a 24-hour sun, okay. And the southern, okay, this is the sun. Well, if you're on the southern hemisphere, that is below the perspective, okay, because it's further than the distance it is from the equator, or from the pole to the equator. Once you go past that 10,000 kilometers, it diverges, and things appear to, it's like looking down a hallway. We know what it is, it's parallel lines, but it appears to touch each other. There's a difference between appearing and what's actually happening. We know the hallway is the same height as what it is at the end, but it's like a postage stamp, it's tiny. Okay, it converges. The sky rolls like a scroll. Okay, it's like you're in a bird cage. And when you go north to south, this is what happens. In a simulation, you can't say it can't work in a simulation, it can. Because you can keep running on that flat surface, and that's basically what's happening. Okay. So, but doesn't matter in the northern hemisphere as well. Okay, this is the northern hemisphere when you're 10 degrees. Okay, let's have a look at the sun angles. Okay, when you're 10 degrees, they're the sun angles for the equinox, the summertime, and the winter time. Okay, 20 degrees, because if we look on this end, okay, we go on 20 degrees below the horizon. This is 20 degrees above the horizon. The center is you. That's why an equatorial mount works, is because wherever you are on the plane, you are in the center. Okay, if you're in the same location as what I'm in, we're both going to get the exact same observation. You understand that? And depending on where you are on that Earth, 90 degrees is always up. So you always, the ground is moving and the sky is moving at the same time. Okay, you understand that? Going from the north to the south. A simulation can work like that. That's plain and simple. Your perspective on how it works is that the Earth is a tiny little speck within this sphere, okay, and the angle of the Earth, when I walk to the pole star, the angle of the Earth is 10 degrees now, okay. That little tiny pinhead in the center, the angle of it will be like that. Now I'm at 20 degrees and 30 degrees and 40 degrees and 50, until I get to underneath the pole star. You're basically saying that's the angle of the Earth, until we go back to the equator on the other side. Well, then it's upside down. Well, this is north and that is south. That actually flips if you go up the other way. So it would feel like north is south and south is north. But anyway, that's why I believe it's a simulation, but it definitely can work in a simulation. Okay, you can't say it can't work, because it can. That's a simple demonstration of how it can work. Thanks for watching. Okay, I wanted to make a video to show how you can measure perspective. What I call bent space, what ball earthers call curvature. Okay, it's simple. You can actually measure the curvature of this straight horizon. Okay, even though it's flat level, you can get a ruler and you can measure it up. It's flat level, but we're going to measure the curvature in this flat line. Okay, and the way you do that is by angles. Okay, because the distance from here to here is the same distance as from here to here with perspective. Okay, if you draw it on a 3D diagram, this measurements, okay, and you get the angles on a two-dimensional piece of paper, because x distance, okay, and the angles to those distances from the distance from here to here and from here to here should line up, okay. But because you have perspective, okay, like how a road goes to a point, okay, well, if this road continued on dead straight and dead straight, well, then therefore you don't have perspective. You have 3 dimensions, okay. You understand that? So basically, if you go and measure a tower, okay, one tower, you can get it on Google Earth, and you can measure the angle to another tower, okay, and then you can measure the distance between those 2 towers, okay. You can get the angle from where you're standing, okay. You understand that? Well, because you have perspective, what happens is things converge in. So what happens is this angle will actually be this angle, when I can find my pen. Well, it will be from here to this point, and from here to this point. The angle will be different, okay? Even though this is the actual length, the same with the road, okay, this is the actual length, and when you look down the horizon, that is the actual length, but it's not. That's because you have perspective. You understand that? The distance of this point, for example, this road is 10 meters wide. Well, the distance of this point is 10 meters wide. Do you understand that? That's because you're measuring bent space, perspective. You're not measuring curvature. The road isn't curvature in, it's perspective. Okay. Anyway, there's a little demonstration and a little experiment for you to do, and you can see that you can measure bent space. You can actually measure the horizon, the flat horizon, the curvature in the flat horizon. Anyway, thanks for watching. Okay, there, critical thing. I did make a video back in, let's work out when we made this video, September 22, 2017. So good over a year ago, about how weight changes due to magnetism. Okay, that's the video that I made. Alright. I also made another video about how the compass works. Okay, back in September 24, 2017, how the South Pole actually attracts to the South Pole needle. Here at 34 degrees south, the actual compass actually nearly hits the bottom. The actual compass needle actually nearly hits the bottom of the plastic. Well, if you listen to what this guy actually says, okay, this guy's in Antarctica, and he shows you exactly how the compass needle gets attracted to the back at the bottom of the plastic. When he turns around, the needle keeps following him because it's touching the bottom of the actual compass. That's because you have an attraction. Okay, so anything magnetic, anything that's metal, is going to weigh heavier due to the attraction of the South Pole. Same with at the North Pole. Okay, and let's listen to what he actually has to say.
South pole is going to be where the magnetic pole lines up, and just so happens that the magnetic South Pole right now isn't even on the continent of Antarctica. It's off of Antarctica, and there's a thing called declination. That's the difference between the two, geographic and magnetic. Currently it's about 140 degrees difference, which means that if your compass did work, it would lead you in almost the complete opposite direction. So I thought I'd show you this though. Here's my compass, and you can see that white needle is pointing down. Look at as I'm
It's attracted to the ground.
That compass doesn't even spin. The needle stays the same. That white needle is dragging down on the bottom of the compass.
That's because the magnetic field is pulling it down.
But not real useful. I mean, you could rotate it around and try to get that off of the bottom of the compass, but for the most part, not real useful. And are you traveling?
You understand that? So what he's basically saying is the compass needle touches the bottom of the compass. So what is actually happening is because the magnetic field strength in that area, in the soil, in the ground, is actually attracting that needle to the ground, the southern side of the needle. If you watched the demonstration from 2 years ago nearly, I actually demonstrated this without even needing to go to the South Pole, and this guy actually went to the South Pole and demonstrated it and proved it. Well, I didn't need to do that. I knew because I understand science. But anyway, I got 10 thumbs down that didn't understand it. I just clearly explained it in a simple demonstration. Thanks for watching. Okay, you two globers, you reckon it's the compass. You have a northern hemisphere compass. Well, here's two compasses. One's had a reversed polarity. Do you even know how to reverse the polarity on a compass? How do you change the magnetic field within that compass needle so it reverses? So south is actually this one here. This is a correct compass, okay? This is a reversed polarity compass, so the north needle actually points south. Okay? You understand that? You see how the north needles are pointing at each other? Okay, well if you look on the perspective on the side, okay, well guess what? Both needles are pointing towards the southern pole. It's got nothing to do with a magnetic northern hemisphere fucking compass. The needle itself is a magnetic field. I can change the magnetic field within the needle to change so the north faces south. Do you understand that? It's got nothing to do with the magnetic northern hemisphere compass. It's all to do with the magnetics within that needle, and I can change the magnetics within that needle. So why don't you two globers show in a demonstration how you reverse the needle of a compass, if you're so intelligent? I mean, I'd just like to see that. It's a simple demonstration, easily to do. Let's see if you can do it. Show me how you can do it. Explain it, video record it, and demonstrate it. Like I said, it's got nothing to do with a northern hemisphere compass. It has everything to do with magnetics, and something that you don't really understand. I can change the magnetics within the compass needle. That's why you have a north facing a north and a south facing a south. Okay, we can put that over there and put that over there. They're both going to swing around. You see that? This one's facing north. Whoa, north is the opposite way. Oh, hang on a minute, what's going on there? That's because it's a reverse polarity compass. Anyway, thanks for watching, boys. Okay, welcome everyone.